Buenos días. Good morning. We are going to proceed to the doctoral defense of Mathieu ROBIN. Sorry for the horrible pronunciation of your name. The thesis is entitled Thesis Segmentation of Electrical Grid to Improve Power System Stability and has been supervised by Dr. Javier Renedo and Dr. Aurelio García Cerrada and Dr. Juan González. In the examination panel, we will have 5 members, as you can see. We have Dr. Marina Oluic, again, bad pronunciation from PK, the Swedish National Grid. We also have on my right Dr. Jef Beerten from KU Leuven. Also Dr. Maider Santos Múgica from Tecnalia Research, and Lukas Sigrist from the local university, the Universidad Pontifical de Comillas, and myself, Oriol Gomis from the Technical University of Catalonia. The session will start with a presentation from the candidate, and after that we'll continue with a discussion where members of the examination panel and also the audience will be able to discuss with the candidate. And yeah, before starting, also I will give the word to our secretary, Lukas Sigrist.
Okay, I just have to read an extract of regulation. I will do that in Spanish, also already in Spanish, to ensure that everything is said correctly. Extracto de las normas de doctorado, evaluación y defensa de la tesis doctoral. La tesis doctoral se evaluará en el acto de defensa que tendrá lugar en sesión pública y consistirá en la exposición y defensa por el doctorando del trabajo de investigación elaborado ante los miembros del tribunal. Los doctores presentes en el acto público podrán formular cuestiones en el momento y forma que señale el presidente del tribunal, Oriol. El tribunal emitirá un informe y la calificación global concedida a la tesis de acuerdo con la siguiente escala: no apto, aprobado, notable, sobresaliente. El tribunal podrá proponer que la tesis obtenga la mención de cum laude si se emite en tal sentido el voto secreto positivo por unanimidad. La universidad habilitará los mecanismos precisos para la materialización de la concesión final de dicha mención, garantizando que el escrutinio de los votos para dicha concesión se realice en sesión diferente de la correspondiente a la defensa de la tesis doctoral. Sobre el premio extraordinario de doctorado. Podrá concederse el premio extraordinario de doctorado anual a aquellas tesis que resulten especialmente meritorias y que hayan obtenido la calificación máxima, con una propuesta de premio extraordinario por cada 10 tesis doctorales defendidas por programa. En caso de que no se alcance el número mínimo de 10 tesis en un curso académico, las tesis candidatas se acumularán para el curso siguiente. Terminada la defensa de cada miembro del tribunal su parecer sobre si dicha tesis debería ser acreedora del premio en cuestión, así como, en su caso, una evaluación de la misma de acuerdo con la rúbrica que establezca cada programa. En sobre cerrado y de forma secreta y anónima, cada miembro emitirá su opinión. El secretario del tribunal recogerá los sobres y los hará llegar a la Escuela Internacional de Doctorado. Las comisiones académicas de los programas elaborarán las rúbricas necesarias para evaluar la tesis doctorales candidatas. La Comisión General de Doctorado, en sesión ordinaria y a la vista de las opiniones recabadas de los diferentes miembros de los tribunales de tesis y de los informes razonados de las distintas comisiones académicas, otorgará los premios extraordinarios de doctorado a la mejor tesis doctoral defendida durante el curso periodo en el programa que toque. Esta distinción se reflejará como diligencia en el reverso del título del alumno.
Okay. Thank you very much for the reading. And now it's time to start with the defense. So you have the word, and you can start with the presentation.
So thank you very much for your introductions. Good morning, everyone. I am Mathieu ROBIN, and today I'm going to present you my PhD thesis entitled Thesis Segmentation of Electrical Grids to Improve Process Stability. This PhD thesis has been supervised by Dr. Javier Renedo, Professor Aurelio García, Dr. Juan González, and it has been done with the collaboration of Dr. Abdelkrim Benchaïb. So to dive into the subject and to define the concept of desegmentation, I present you this conceptual electricity network, which is composed of different regions that could be different countries, so different electrical grids that are connected together by both AC and DC link. Since they are connected by AC link, all of them are synchronous together, so we have one big AC synchronous region. Let's now imagine that for some reason, we want to replace the AC link connecting the different regions by DC link. In this case, the different regions will become asynchronous to one another, but they will stay connected by the DC link. So this action to go from one big AC system to a set of AC asynchronous systems connected together by DC link is what we call DC segmentation. In other words, DC segmentation involves breaking large grids into smaller AC sectors interconnected by HVDC transmission line. It is important to note that this segmentation it must not be mixed with control actions or temporary measures, such as international ice landing, because this segmentation is a planning action. It's a permanent measure that will strongly affect the power system. That will strongly affect the power system. This PhD focus on desegmentation and the impact of desegmentation on the stability of AC/DC power system. Desegmentation may seem to be going against the evolution of the grid. Indeed, in the last decades, we've tried to connect bigger and bigger AC synchronous grid, with the last example being in continental Europe, the connection of the Ukrainian electrical grid to the continental Europe, and soon to be the connection of the Baltic countries. However, we also see, in more recent years, we also seen the use of more and more DC link to interconnect the grid, and in this context, desegmentation is much more natural. So here is an example of southern China. Up to 2016, southern China was one AC synchronous system, and we had a big flow from the west to the east, so from Hunan region to Guangdong region, and it was done by AC and DC link, but mainly by DC link, and they realized that a contingency in one of the DC link could potentially overload the parallel inter-area AC line. And because of that, they decided to disconnect the AC line connecting the Hunan region to the first documented case of desegmentation of a power system. So as you see, desegmentation is actually not science fiction or something like that. So for the table of content, I will continue the introduction with some state of the art. Then I will speak about desegmentation and power system stability, dominant electromechanical oscillation paths, algorithm for desegmentation to mitigate electromechanical oscillations, desegmentation and supervised controllers, and I will finish with the conclusions. This table of contents follows the three main questions we try to answer about desegmentation. So the first one is why should we desegment the power system? So what are the advantages of desegmentation? What are the advantages and disadvantages of desegmentation? Where to desegment the power system? So what segmentation boundaries should we choose? So which AC line should be replaced to DC in order to reach segmentation for one given power system? And the last question, how to create a desegmented system? So once we have this desegmented power system, how do we control the DC links? In general, we know that from the literature, we know that the main driver for VSC HVDC links, because this PhD uses only VSC HVDC links. So the main driver for this, the creation of this link is to increase or even just to allow power exchange capacity between regions. So it can be used for the transmission of bulk power via overhead line for long distances, transmission of bulk power via to long distances, or the connection of asynchronous power network, as it is nearly the only solution to do so. New VSC HVDC links can be built from scratch, but they can also be built using existing AC line. And so by doing this upgrade of an AC line to DC, we also increase the power exchange capacity. And such project is currently undergoing in Germany and called the Alternate project. So first question, why should we desegment a power system? First thing, desegmentation has a potential to increase power exchange capacity. Naturally, to do desegmentation, we'll need to add some new DC link or to upgrade some AC link to DC. As I say, that increases the power exchange capacity, but also by the control of the DC link. Indeed, when an interconnection is done by AC lines, we always need to keep an important stability margin. And if this interconnection, in the case of desegmentation, is not only by DC link, as the DC link are fully controllable, we don't need to keep such a big stability margin, so we can use better the full capacity of the line. In the literature, subjects have been already quite studied about desegmentation is desegmentation and for blackouts. And the main finding is that desegmentation can lower the risk of large-scale blackouts. There have been other literature on the subject of desegmentation, but not so much, and mainly preliminary studies, let's say. Some of them described desegmentation as a grid-sharp absorber, as it can limit the propagation of the fault. They also identified that desegmentation can increase the angle stability margins of the system. However, when done with fixed power references, it can just. And so in this PhD, we'll aim to assess the impact of desegmentation on the dynamic performances of a power system, as it has not been fully studied yet. And when we speak about power system, we speak about angle stability under large disturbances or transient stability, small signal angle stability or electromechanical oscillations, and frequency stability. For the second question, where to desegment a power system? So for this question, there have been really little research. There is one study that compares different segmentation boundaries with the objective to limit the communication failure of line commutated converters. But this research, like the other one, do not justify the initial choice of segmentation for selecting these boundaries. And in our case, we aim to mitigate electrical. And to do this algorithm, we use the concept of dominant interior electromechanical oscillation path presented in the literature. So to summarize the state of the art, on the first question, why to desegment a power system, there have been a few literature, mostly on the reduction of faults, but also the reduction of propagation of a fault, and some study on the transient stability and frequency stability. On where to desegment a power system, there have been really little study, and none of them justifies the initial choice of desegmentation. And I haven't shown it, but on how to appropriate a desegment system, I haven't shown it because there already a lot of literature, but this literature focuses on different, so there is a lot of literature on the supplementary controller for DC link, either in the case of embedded DC link or DC link between. Nearly none of them focus on a segmented system. So the identified scientific gaps are the following. So on why to desegment a power system, we aim to assess the impact of desegmentation on large power system dynamics. For why to desegment a power system, we aim to propose a method for selecting the best segmentation boundaries, and we try to focus on the mitigation of electromechanical oscillation. And on how to play the segment system, we propose to apply some of the existing supplementary controllers to the context of desegmentation in order to further improve the stability of a desegmented test system and to add value to desegmentation. So, desegmentation and power system stability. So what are the impacts of desegmentation on power system stability? So the contour true area test system. And I will compare two cases, so the initial AC base case and the desegmented case. For the desegmented case, the AC transmission line are replaced by a VSC HVDC link, which is controlled in grid following, as I will always do in this PhD. And in this case, the HVDC link is controlled with constant power references. We start by doing a short circuit fault at bus 6, so on the left of on region 1 of the system, let's say. And we observe the following. So on the top, you have the result for the AC base case, and on the bottom, the result for the DC segmented case. And on the left, we observe the frequency difference between generator 1 and generator 3, so two generators for different regions. And on the right, the angle difference between the generators of the same region. So in red, generator 1 and 2, in blue, sorry, and in red, generator 3 and 4. The first observation, in the case of the AC system, we have a huge angle difference between the two regions. And so in a real life system, there will be some protection that will be tripped really fast. So it could be pole slip protection, speed protection, or even the overloading of a line. So anyway, the AC base case has a loss of synchronism. In the case of desegmentation, we also have a big angle difference between generator 1 and 3, but in a way it doesn't matter because these two generators are in asynchronous regions. To see if the system stays in synchronous, we need to look at the angle difference between the generator of the same region, and we see that we have some oscillation, but it's well bounded and well damped. So the system stays stable in the case of desegmentation. So with desegmentation, we have the separation of the inter-area singulation constraint and a strong increase of the critical fault clearing time. So desegmentation is beneficial for churn stability. For small signal stability, we do the same fault, but with a much shorter time duration. And in this case, we suppress the power system stabilizer of the generators in order to better see the oscillations. On the right, again, we have the angle difference between generators of the same region. And on the left, we have the frequency of the 4 generators. The first thing we see is that in the AC base case, we have generator 1 and 2 oscillating against generator 3 and 4, which means we have badly damped inter-area oscillations, and with a frequency of 0.5 Hz, more or less. For the DC segmented case, this oscillation completely disappears, and we still see some local oscillations that are well damped. Here we cannot compare with the AC case because in the AC case the inter-area oscillation is too big. But from small signal stability that I don't represent here, I can tell you that the damping is similar for the two cases for the local oscillations. So we have the superposition of the inter-area oscillations, and the local oscillation remains. So the segmentation is also beneficial. For frequency stability, this time we simulate a loss of generation, which is actually a connection of a load. Again, on the left, we observe the frequency of the generators, and on the right, the power exchange between the two regions. First thing we can say is that in the case of desegmentation, generator 3 and 4, so the non-faulty region, is not affected at all by the fault. So desegmentation stops the propagation of the fault. However, we also see that in the case of desegmentation, the two other generators see a much bigger frequency deviation than in the AC base case. So desegmentation is more critical for frequency stability, and that's because the DC link, since it is controlled with fixed power references, it didn't allow the finite reserve between the two areas. So to conclude, we have desegmentation with fixed power references that improve trend stability of the overall system. It also improves small signal angle stability of the system by removing the inter-area oscillation without impacting the local ones. And however, it jeopardizes the frequency stability of the system. For this last point, we'll try to mitigate this issue through super-oriented controllers, as we'll see in part 4 of today's presentation. All of these results have been the subject of conference that have been conference paper been presented at the ACDC 2021 conference. So now let's speak about dominant electromechanical oscillation. Why should we speak about them? So we have seen, from the literature, I haven't shown it in detail, but from the literature, we know that small signal stability is an issue in large power systems. We have also seen, just before, that desegmentation has a potential to structurally stop inter-area oscillations. So if we properly choose the desegmentation architecture or boundaries, we will stop the problematic oscillations. So to do so, we have developed an algorithm that for a given AC power system propose a desegmentation architecture to stop these oscillations. This algorithm is presented in part 3, so in the next part of the presentation. First, we had to understand how the oscillation propagates to the system, and so we have developed the first algorithm that identifies the dominant electromechanical oscillation path, and that's the part I'm presenting you now. So why should we need such an algorithm? So here is a simple 6-generator test system, and for this algorithm, it's quite obvious it's quite straightforward that there is an inter-area oscillation, and if there is such inter oscillation, it will be naturally generator 1, 2, and 3, oscillating generator 4, 5, and 6. Inter oscillation, the main path will be the one between generator 1 and 6. There are the two generators at the extremity of the system. And it's of course straightforward that if we want to stop the inter oscillation, we need to cut the path, this path more or less in the middle. However, for a more complex test system, I took, for example, the Nordic 32 test system. It's really not obvious at all to say what will be the main interior oscillation. Even if we have identified it, it won't be obvious to know exactly the main interior oscillation path. And actually, there will be more than one. And it also, even if we identify them, it won't be straightforward to know which one, where we should cut them. So that's why we need an algorithm to identify those paths. So to do this path, we need to linearize the system. So we need to do some small-scale analysis. With this small-scale analysis, we have the free response of the system. So we have the state vector x, the derivative of state vector x, which is equal to the product, the state matrix A, and the state vector itself. And we have the output vector y, which is the C by the state vector. For this system, we have the eigenvalue lambda k, which is the result of the solution of this equation, with vk, the right eigenvector of the mode of the system. I won't get into more equations, but with this small analysis, if we focus on one given mode, which in our case will be the interior mode naturally, so if we focus on one given mode corresponding to the eigenvalue lambda k, we can obtain interesting data from the small analysis. So we can the mode shape and the observability factor. The mode shape tell us how the state variables are affected by the mode, and the observability factor tell us how the output. Mode shape and observability factor are both complex numbers, and they are usually defined by their phase and magnitude. In this study, we'll use the mode shape associated to the speed of the generators to identify the observability vector of the bus frequency and the bus current to identify the dominant oscillation path. So let's go back to our conceptual 6-generator system to explain a bit more. We carry out small analysis of this test system. We identified badly done focus on the study of this mode. We measure the mode shape associated to the speed of the generators in this mode, so that tells us how the speed of the generators are affected by the mode. We can show them with a table with magnitude and phase, or we can show them in a complex panel. From the phase of this mode shape, we can see that generator 1, 2, and 3 oscillates against generator 4, 5, and 6, as expected. And for the magnitude, we can say the generators the further away from the middle of the system are the ones that 1 and 6 are the two more oscillating generators in this oscillation, in this mode. And so that leads us to the concept of inter-area oscillation path. So since generator 1 and generator 6 are the most distinct generator, the path with the most oscillation will be the path between generator 1 and generator 6. We plot the bus frequency observability factor along this path, so how the frequency of each bus is affected by the mode. On top, we have the magnitude, and the bottom, we have the phase. From this plot, we can define some characteristics of the inter-area oscillation path. The first one is that we have the edges, so the extremities of the path, that are the two buses with the highest value of bus frequency observative factor in magnitude. We also define the pivot bus as a bus with the lowest value, this time, of bus frequency observative factor, again in magnitude. And we can see that this pivot bus, it's called like that because it divides the path into two groups of buses with opposing phases. And so this means that the buses at each side of this path oscillate against, the frequency of the buses oscillates against each other. So the algorithm for the identification of those paths works in two steps. First step, we identify the edges of the path. So we do that by first identifying the two groups of oscillating generators. And second, in each group, we identify the most oscillating generators. And these two generators will be the edges of the path. Step 2, so once we have the two edges, we find the path between these two edges. And we do that in an incremental manner, so one bus at a time. And we use the branch current observative vector to identify the next branch of the path, and the bus frequency observative vector to validate the next bus. I won't get into more details in the algorithm, but I will implement it, I will compute it, show an example on the Nordic 44 test system. So the Nordic 44 test system is a representation of the electrical grid of the three Nordic countries, Norway, Sweden, and Finland. We carry out small analysis of this test system, and we identified a badly damped inter-area mode, and so we compute the algorithm for this mode. First step, we identify the path edges, so we identify the two oscillating groups of generators, and in each group we identified the most oscillating generators, so the two path edges. And step 2, we identified the path between these two edges. If we plot again the bus frequency observative vector along this path, we can identify the pivot bus, and as we say, as we said already, for the simple test system, it separates the path into two groups of buses with opposing phases. So to conclude on this, on the dominant electromechanical recession path, so we have studied this concept. We have validated the use of bus frequency and branch current observative vector for the identification of this path. However, we have also discarded the use of bus voltage observative vector for this identification, as this data wasn't reliable enough. And this small point, this line, I haven't shown it in the presentation. From this study, we propose an algorithm for the identification of those paths. The algorithm is fully automated and obtains systemically the desired path. We have tested and validated the algorithm using the Nordic 44 test system. And this algorithm will be used for the desegmentation of power system, as I will show you just after. But it could also be used for other applications outside the desegmentation. So now that we have found this path, we can cut them, let's say, so we can develop our algorithm for the desegmentation to mitigate electromechanical oscillations. So if we go back to our 6-generator test system, on the left is a AC base case, and we compare two potential segmentation boundaries. So one just next to the pivot bus of the path, and one more on the side of the path, let's say. And we compare, we do small analysis of the three systems. First observation is that in the case of desegmentation next to the pivot bus, we completely suppress the inter-area mode, and we have no visible impact on the other modes. In the case where we segment on the side of the path, the inter-area mode persists. It has a better damping than in the AC case and a slightly different frequency, but there is still this inter-area mode. And we have no visible impact on the other mode. So desegmentation closer to the pivot bus is better, as it guarantees us to group the generators in the most current way possible, and thus it fully stops the inter-area oscillation. So the algorithm for desegmentation has 3 steps. First, we identify the edges of the path. Second, we identify the dominant path between these two edges. So step 1 and 2 are the algorithms I presented you before. And step 3 is a cutting of a line of the path. For a simple test system that will be enough. But for a more complex mesh system, cutting one line won't be enough to reach the segmentation. So we will have to repeat step 2 and 3. So we add a while loop. Is the system segmented? If yes, the algorithm is finished and it tells us the output, so the line to the desegmentation boundary, so the line to be replaced by DC, the AC line to be replaced by DC link. If not, it repeats step 2 and 3 until desegmentation is reached. Again, we compute this algorithm on the Nordic 44 test system. So we carry out small signal analysis, we identify the badly damped inter-area mode, and we compute the algorithm for this mode. We had step 1, we identify the edges of the path. Step 2, we identified the dominant inter-area path between these two edges with the pivot bus. And step 3, we cut the path next to the pivot bus. However, switching this line to DC won't be enough to reach segmentation, as there is still an AC link possible between generator 1 and generator 2. So we repeat step 2 and 3. We identify the next dominant path with its pivot bus, and we cut it next to the pivot bus. This time, it is enough to reach the segmentation. So the output of the algorithm will be that we need to switch these two AC lines by DC link. So to conclude on this algorithm, we have proposed an algorithm for the segmentation of AC power systems. The algorithm is fully automated and obtained systemically a DC segmentation scheme. It uses the concept of dominant interior oscillation path presented before. We have tested and validated the algorithm on the Nordic 44 test system. And, most important, in the resulting desegmentation system, the initial critical interior oscillation is suppressed without jeopardizing the damping ratio of the local mode, intra-area mode. This slide is pumped. I haven't shown you the result yet, but I will do it just after. These two algorithms and the results that go together have been the subject of a journal paper that have been published in the IEEE Open Access. So now we have said in which cases the segmentation is interesting. We know how to find a desegmentation architecture or desegmentation boundaries. So now that we have a desegmented system, how do we operate him? How do we control the DC links? So we propose to use two supplementary controllers. The first one is a frequency controller. So why a frequency controller? Is because, as I said before, in the case of desegmentation with fixed power references, we have a loss of frequency stability. So with a frequency controller, we'll try to limit this issue. And naturally, the frequency controller will be on active power injections. The second one is a PODQ, so power oscillation damping on reactive power. Why a POD first? It's because we saw that desegmentation stops the inter-area oscillations, but it doesn't impact the local oscillations. So let's try to improve the local oscillations. A POD could be done on active with active power injection or reactive power injections, and we choose the second one, reactive power injection, for two reasons. The first one is to avoid interaction between the two controllers, because the frequency controller is already on active power injections. And the second one, which is the most interesting, is that is to avoid the propagation of perturbation. Indeed, with active power injections, the active power injected at one extremity of the DC link needs to come from the other side. And so, in a way, we'll recouple a bit the system, and we want to avoid that. We want to keep the firewall effect of desegmentation. And in the other end, with reactive power, we don't have this issue because the reactive power injection at the two extremities of a VSC HVDC link are perfectly independent. So for these two controllers, for the frequency support, it's quite actually a simple controller. It's a difference of frequency between the two extremities of the VSC HVDC link. For the POD Q control, it's a bit more complex. It's also based on the difference of frequency. And this time is the difference between a reference frequency and the frequency of the connection point of the VSC. To choose this reference frequency, we had different solutions, and we choose to compare two of them. The first one is to use the local frequency of 50 Hertz. And in this case, we'll only need local measurements. So we'll speak about PODQ, local frequency. The second case is to use the frequency, the average frequency of the system. In our case, in the case of the segmentation, using the average frequency of the full system doesn't make sense because we have an asynchronous system. And so we use the average frequency of all of the generators in the region at which the VSC is connected. And in this case, we speak about PODQ, frequency of center of inertia. Our case study is a Nordic 44 test system, and we compare four cases. The first one is AC base case. The second one is a DC segmented system as proposed by our algorithm. As I said, we are always with VSC HVDC link and always in grid following. And for this case, the DC link are controlled with fixed power references. The third case, we add our supplementary controller, and we add both the frequency support controller and the PODQ. And for the PODQ, we choose a local frequency. The fourth case is really similar to the third, except that the PODQ this time is with the frequency of the center of inertia. For simplicity, we'll speak about region 1 for the cluster of South Norway and region 2 for the rest of the system. For the PODQ, they aim to dump the local mode, but we need to choose which ones because there is a lot of them. And of course, we choose the least dumped one. So the VSC of region 1 will aim at dumping mode 2, and the VSC of region 2 will aim at dumping mode 4. We do a comparison of the fourth system with small signal analysis. The first observation is that the inter-area mode is fully surprised by desegmentation, without or with supplementary controllers. The second observation is that mode 2, so the local mode of region 1, is well improved with the PODQ. And mode 4 is also improved by the PODQ, but a bit less. It's important to note that all the other modes are not changed or barely changed, barely affected by neither the desegmentation or the supplementary controllers. And also interesting to note that the two control cases have similar results. Let's now confirm that with dynamic simulation. So we simulate a loss of a line in region 1. Here is a loss of a line. And we will plot the frequency of two representative generators, so one frequency of each region at the two extremities of the system. So here's the frequency of our two generators. We first focus on the region 2, so on the non-faulty region. And the observation is that only the blue curve has strong variations. And that means only the AC base case, which means that this segmentation blocked the propagation of the fault. Now we can also see that the blue curve, so the AC base case, sees some inter-area oscillation, some oscillation between the two generators, which is not the case in segmentation without or with supplementary controllers. So segmentation suppresses the inter-area oscillation. If we focus on the faulty regions this time, it's a bit harder to see, but let's try to look a bit at the local mode. So if we compare the red curve, so no supplementary controller, to the two other one, we can see that the red curve has an oscillation which is less damped than the two other curves. So the PODQ dumps the remaining oscillation, but I have to say it's not so easy to see, and that's why we also did the small signal analysis naturally. So that was for the effect of desegmentation and PODQ for electromechanical oscillations. Let's now look at the effect of desegmentation and supplementary controller to the frequency stability. This time we simulate a loss of generator still in region 1, and we select the biggest generator of the region. We again observe the same frequencies. We again observe the same frequencies. The first observation is that the blue curve, so the AC1, has the lowest frequency deviation. So frequency stability deteriorates in the desegmented case. Second observation, if we compare the different desegmentation case, is that we have a bigger frequency deviation, a bigger nadir, in the case of desegmentation with no supplementary controller. So that's confirmed that the frequency support controller mitigates the issue, without being as good as the initial AC case for frequency stability. So to conclude, for small signal angle stability, desegmentation can be very effective to suppress critical inter-area oscillations. With constant power references, it does not impact the local mode. However, PODQ can dump the local mode. Both PODQ with local frequency and with the frequency of inertia produce a good result. And so because of that, maybe PODQ with local frequency is better, because in a real-life system, it's much easier to put in place, because there is need of less measurement, and there is no need of communication. For frequency stability, so with respect to the original AEC case, frequency stability deteriorates with desegmentation when we have constant power references. We mitigate this issue with the frequency support controller, even if it's still not as good as the AC-based case. So altogether, the use of desegmentation, frequency support, and PODQ brought an important improvement to the overall stability compared to the initial AC case. So all of these results on the supplementary controller have been the subject of another journal paper that have been published really recently at the International Journal of Electrical Power and Energy Systems. So, let's now conclude the full PhD. Before going to more traditional conclusions, I wanted to show you, to give you a full picture of the PhD, a full picture of the work stream of the PhD. So first, we started with some test system, so with benchmark grid. We started with the Condor Terraria test system. We will simulate it using the Daimola environment. And under Daimola, we use two libraries, OpenIPSL for the AC components, and because OpenIPSL doesn't have the DC component we needed, we have developed internally in Supergreen Institute an HVDC library. For a small error of appearance, but no issue. To do this simulation, we needed the dynamic model and the power flow data of our models, of our test system. We use Daimola and MATLAB to do some small signal analysis, so linearization and eigenvalue analysis of the system. We also use, and mainly use actually, Daimola for time domain simulation, and that was mainly loss of a line, charge circuit, and loss of a generator. With all of that simulation, we could study the effects of desegmentation on the stability of power system, and initially it was only with constant power references, and that was part one of today's presentation. Then we decided to work on a more complex test system, so the Nordic 44 test system. We decided to use we needed to use another tool, which is SSST, which is a MATLAB-based tool internally developed into the IIT of Comillas University. It allows us to do a detailed small signal analysis with a full processing, eigenvalue, mode shape, observative vectors, sensitivities, and much more things that I didn't use in this work. To do this small signal analysis, we need naturally the static data and the dynamic data of our models. And we use the output of this analysis for our algorithm for the desegmentation of power system. This algorithm has two outputs. First, the dominant inter-area oscillation path, and that was part 2 of today's presentation. And second, the desegmentation boundaries. And with these new desegmentation boundaries, we could update our test system and repeat the simulations. and studies the effect of segmentation on stability of power system with constant power references, but with a more complex system. And all of that was part 3 of today's presentation. Then we decided that we could improve further, to see if we could improve further the segmentation, so if we could further improve the stability of the desegmented test system. And so we added 2 supervised controllers, so PODQ and frequency support controllers, and that's been implemented in our test system. And we followed that. We could study the effect of segmentation or stability of power system with supplementary controllers, and that was part 4 of today's presentation. So for the more traditional conclusion, we have studied the effect of the segmentation of power system stability. We have found an improvement of run stability by the suppression of the inter-area synchronization constraint. We have seen an improvement of small signal angle stability by the suppression of the inter-area mode and the dumping of the local mode with the PODQ. Sorry. For frequency stability, we have this segmentation jeopardize a bit jeopardize the stability, but frequency support mitigates the issue. And the second part, and maybe the main part, was the algorithm for the segmentation of power system. So the algorithm has 2 steps. So the identification of dominant electromechanization path. So we have proposed a fully automated algorithm for this identification process, and we have proposed a desegmentation of the system to suppress the targeted inter-area mode. So the contribution of the PhD thesis is the following. So we have analyzed the impact of desegmentation with constant power standpoint on electromechanical oscillation, trend stability, and frequency stability. We have proposed an algorithm for the automated detection of dominant inter-area electromechanical oscillation path in an AC power system. We have developed an algorithm for desegmentation to mitigate electromechanical. It is, and so we have identified the case spec to be used for such study. And we have proposed the algorithm. And for supplementary controllers, so we have used 3 supplementary controllers. Frequency support controller, PODQ on local frequency, and PODQ of the frequency of inertia. The 2 first are, all of them are from the literature, but the last one needed some adaptation for our cases. But the main contribution is that we have implemented these 3 supplementary controllers in the particular context of the segmentation, and to the best of our knowledge, it's the first time it has been done. So, still for the contribution, as I told you, we have 3 papers published, so 1 conference paper and 2 journal papers. And so that was all for my own work, but there is still much more that could be done. For the architecture of segmentation, as you have seen, we worked only using point-to-point DC links, so we could use empty DC grids. We could also segment the system in more than 2 regions. For the algorithm for the segmentation, we focused on electromechanical oscillation, but we can also try to set the algorithm for trend stability or also frequency stability. And also, this algorithm could be used for other applications outside of the segmentation, such as international landing or the placement of embedded DC links, wider area measurement system, or even PSS. Even PSS are widely used already. And for the control of a desegment system, we used only some supplementary controllers. We could add many others, such as AC voltage control, emergency power control, POD on active power system, static inertia, and so on. If we have many controllers, of course, we need to coordinate them. And this PhD focused on grid-following VSC only, and so we could also study on grid-forming control. But that's only if we focus on power system stability. Actually, desegmentation could add value to the power system for many more things. It could, as I say, in the state of the art, it can also impact the reduction of blackout. It could also improve market operation, mainly if the segmentation boundary correspond to the market boundaries. It can also be used to improve power exchange capacity, and maybe to improve or to control the power flow in the region next to the segmentation boundary. And I spoke mainly about the advantages of segmentation, but the main disadvantage, of course, is the cost of the DC link, and so there is a need to do a cost analysis of the segmentation. And I think that actually what's the most interesting about segmentation is that it opens a full new perspective on the PROAS system, because there is, let's say, a change of paradigm for the electrical grid. We've seen in the last decades that we connect together bigger and bigger synchronous regions. And now, for some stability reason, we say that maybe we should resegment a bit the grid. But it's not going backwards to segment the grid, because with the DC link, we gain a lot of controllability, since the DC link are controllable while the AC one are not. And so it opens a lot of possibility to rethink how the system is operated. So thank you very much. That was all for my presentation, and I'm listening for your questions.
Okay, thanks. Thank you. Thank you very much for the presentation. Now we will proceed to the discussion. We will follow the order I have here in the list, which also corresponds to the distance of the different panel members from the university. Okay, so we will start with Dr. Marina Oluic, then we will continue with Jef Beerten, then Maider Santos, Lukas, and finally I will close myself. So we can start.
Thank you, Professor Gomis Bellmunt. Thank you, Mathieu, for a very good presentation and a summary of the work you carried out during your PhD journey. It was a pleasure to read your thesis, the monograph. It was a well-structured, clearly written work that addresses timely topic, presents interesting results. So I enjoyed a lot while following how you carry out a thorough literature study, so identify the research front and then identify the research gaps, so the focus points, and to move this front and provide your contribution with interesting results. And I would really like to commend you for this work, and also your supervisors for the good leadership and overall very good work.
Thank you.
So perhaps as an introduction to this discussion and questions from the committee, I would start on a very high level. So something that you also touched upon in your thesis. So we have this historical development of AC networks becoming larger. So we have, let's say, a continental Europe network size. So if you could perhaps reflect upon why we don't see that much this distributed grid concept today, we still have these larger interconnections. And perhaps while doing that, think or share your thoughts on the AC system scale where the advantages of your approach is the most prominent. So you mentioned in the introduction something about the perfect size. And perhaps while sharing your thoughts, think about this cost-benefit analysis. You later also mentioned that, and that this is a planning action and so on. I'm just thinking about the cost of, let's say, we have this Southwest link that you also put in your table in the introduction in Sweden. And if I convert that maybe to euros, it's around 600 million euros project. So if you could start with this type of overview. And the prospects of the
Yes, so actually, if money was not an issue, we would put DC link everywhere nearly, because we gain a lot of controllability, we gain power exchange capacity. So there is nearly only advantages on the technical aspects, but the price is huge, and we have many links that reach the billion cost. So I think the main reasons to do this segmentation is in the case where we have big distances, and because that creates oscillations, and maybe mainly in the case where we already have interconnection that is mainly done by DC link. So I use the example of thought of China, but I like to use the example between France and Spain, because I did my PhD between these two countries. But along the Pyrenees, historically we have 4 AC lines that total 2 gigawatts. And some decade ago, more or less, there have been the creation of a DC link in the east part of the Pyrenees, so in Catalan country, of also 2 gigawatts. So now we have half of the interconnections that are not done by DC and half by AC. And in the coming years, in theory, we'll have a new DC link on the west part of also 2 gigawatts. And so we tend in the direction to have some interconnections that are mainly done by DC and not by AC anymore. And even if we have just one AC line, it's bound us to stay in synchronism, which is a strong constraint. And so at some point, we may think, why keep this small canal of power exchange if we have a much bigger, which is more controllable and can bring much more tool. But of course, just cutting the AC line is a loss, and replacing and upgrading them to DC is a cost. So there is a big issue with that. So for a really well dense and meshed AC system with not so huge distancing and so much oscillations, this segmentation is not necessarily a good idea. For a small test system with low inertia, this segmentation is also not a good idea. But for a system with for a big AC system with already a lot of embedded DC link and some electromechanical oscillations issue, this segmentation will certainly be a good idea.
Thank you. And if we proceed through the thesis, already in your introduction, you're mentioning how traditionally we're damping electromechanical oscillations, so listing PSS and POD on FACS and HVDC devices. Mm-hmm. Are you aware of some other sources of POD functionality or regulatory framework that supports this, at least in Europe?
Not really, actually.
Let's say with the power park modules, so connected via converters.
But we also have POD on the connection of renewable energy sources that are linked by DC.
Exactly. So we have, we could have that if we see that it is needed in the system. So we have a good framework that supports us in putting forward these requirements. I believe you also mentioned that later. But, yeah. And something perhaps you mentioned why you use PODQ and not PODP, and then you mentioned some reasons behind that, too, actually. So the first one, PODP is done by modulating P, meaning in, let's say, a D-segmented case, you mentioned that this could lead to a propagation of a disbalance or a fault. But then you also use a frequency regulator later, which is the same loop, so from frequency to power. And you mentioned later on in the conclusions that this does not have a negative effect. So it not completely works as a firewall when we have this type of controller, frequency controller. So that's the first question, because we think that PODP is a very effective method to damp the oscillations. So if you could perhaps comment on that. And the other reason that you mentioned is the interaction between the controllers. If we use a PODP, then I would challenge that and say, okay, if we use PODQ and we have a voltage regulation, is there also risk for the interaction? So if you could reflect, you mentioned also PODP as something to tackle next, and PODQ is something that the majority of actors connecting is the first solution they want to provide. So they would like to avoid to modulate P if possible for these purposes. But
yes,
do you have some thoughts on that?
Anyway, if we use active power, whatever the super controller is, we may propagate a bit the maybe not oscillations, but at least some perturbations. And that will depend of the gain of the controller and also of the filter that we have. And we saw with the frequency support that it can be mitigated to a really small perturbation and a really smooth perturbation in a way, and not oscillations. And so the difference with the main difference between a frequency support controller and PODP will be that frequency support controller is a bit more smooth in a way. It goes only in one direction, while the PODP will bring a lot of small oscillations naturally, and so that may trigger some small issues in the system. But I think that with a proper choice of parameter, the issue should not be too important actually.
Mm-hmm. So one could have some kind of trade-off between frequency support and also damping of oscillation by modulating active power, for instance, some kind of controller that takes into account both within the same control loop. It's the same for the PODQ with the voltage regulation.
Yes.
We need to make this trade-off between the functionality performances. So, yes, and something perhaps that you in relating to chapter 3 and the modeling. So you have a number of assumptions because we need to make these simplifications when we're carrying out the research and so on. So I'm just wondering, some of them that I listed here is like the absence of frequency-dependent loads, neglecting converter losses, considering RMS models of MMC and two-level VSC as equivalent, then PLL and the inner control loop, closed loop time responses. So you have certain values for these time responses. Then you use the open loop strategy for the DQ reference currents. Then you treat separately HVC, HVDC in this hybrid initialization, and so on. So which one of the assumptions that or premises that you had you would perhaps think is the most critical and the first one like to work on and improve that aspect? Because this is completely understandable. We do a lot of simplifications, those that and modeling that is good enough to sufficient for analysis of a certain phenomenon. So do you see some aspect where you could
so actually the AC system is fully RMS, and so our modeling of the DC link and the VSC is a bit more detailed than the most basic RMS modeling. And so we did that. The first reason was simply because we had them available. And so if we have a bit more detailed model already available and the time of computation is not too big, of course we use them, because like that we are sure not to make too strong assumptions. And so I don't think with the type of perturbation I'm seeing, I don't think that the detail, the level of detail of the HVDC of the HVDC link is needs much improvement actually, because it's already a bit more detailed than what we have on the AC side.
Perhaps something about, let's say, the very definition. We talk a lot about inter and intra-area mode. We focus first on the inter-area mode. So did you think about the definition of the two? We usually think in the sense of frequency, but sometimes these frequencies overlap. And then there were some interesting groups of generators, combinations that were like not the most critical inter-area mode, but like less critical, combining, interesting groups of generators. Perhaps, how would you go about this definition? There are different sizes of system, and perhaps another question is about what was your criterion for the loss of synchronism in your nonlinear simulations when you look into the transient stability?
So for the aspect on local inter-area mode, I didn't use the frequency actually much. I use more the geographical aspect, but it's always the point of view, because the local mode in southern Norway, once we have done the desegmentation, it becomes the inter-area of southern Norway. So to me, what matters the most is to focus on the least mode, because they are the most problematic one, and they are usually inter-area mode over big distances. So I use more the geographical criteria of big distances to define the difference between local and inter-area mode, but it's really a question of point of view of the size of the initial system you have. If you focus on one small part of the system, of course, you will focus on more local modes that would become the inter-area one. And for the criteria loss of synchronism, it was angle difference of more than 45 degrees between two generators. Yes.
Okay. Perhaps an example of this question relating to the definition of intra and inter-area mode. So like in table 5.1, so there are some groups, let's say a frequency around 1 Hertz for the oscillations, but then we have let's say a generator 6 and 1 forming one group, and generator 4 and 3 forming another group. So it's a very simple system where we can see this geographical.
Which table it is?
5.1.
Figure 4.
Yeah, table 5. Just to exemplify the complexity,
Page 56.
yes,
Page
page
56.
56. So if we like look, okay, the first mode and the system is very simple, so it's clearly an inter-area mode. But let's say mode 2, for instance, it's a kind of like frequency, let's say in the range that we want our PODs, at least in Sweden, to damp the oscillations. So we talk about 0.25 to 1. That's the requirement we want to see from the actors connecting to our network. So it's, and then we have a generator 4 and 3 in one group, oscillating against
The
6
two
and 1.
extremities.
Yeah, so how do you think about, what are your thoughts on this?
That's an inter-area mode because it has generators of the different regions, but it's a more complex mode in the case or in the context of the inter-area oscillation, and we can't really separate them in a way. So it's an inter-area mode, but with I would say it's like a 3-region mode in a way, with the center and the 2 extremities, as we observe in Europe actually. And so it's one particular type of inter-area mode with more than 2 centers in a way.
Okay, yeah, it's not a easy answer. So it's a bit, but you see this, like you start clearly from like one inter-area mode, and then let's say number 4 is clear, it's within one group, so it is an intra-area mode and so on. So, but then you talk about how do you group the generators, and then how did you decide on this criterion about 45? Is it like half of 90?
Actually,
and then when you define the ascend, the first point, then you have a criterion with the 90 degrees. So how did you decide on these criteria? So what's the reasoning behind?
So the step 1 on the algorithm, whatever which one we speak about, is the identification of the oscillating generators and the 2-path edges. And I need, for my algorithm, I actually don't need the 2 oscillating groups. What I need is only the 2 extremities, the 2 main oscillating generators. So the criteria of 45 degrees is perfectly it could have been 25 or 90 degrees. I mean, 90 degrees, no, but it could be a bit more, it could be a bit less. It doesn't change so much. And so it's just to be sure that I don't have, that I have together the most important generator of each group. I also added another criteria that if one generator has the magnitude of the mode shape under less than a tenth of the most generators, I don't study it, because its participation on the oscillation is too small. And that's this way to choose groups. It works well for clear interior oscillation, but for example, it won't work so well with the interior you enlightened, with the oscillation you enlightened, with more than 2 regions in a way.
Okay, thanks. And perhaps a what if question. So in a figure 518, you simulate the loss of a line. And I'm wondering what would happen if we lost the line on the main path of the oscillation instead. So because this one is like not that one, not on the path. So the one where you later on segment the system. Did you think about this scenario?
Yes, so it depends of the test system. So of course, for a simple test system, that will directly, for a really simple system, it will directly be the loss of synchronicity between the 2 regions because they will be disconnected. So if we focus on a more mesh system, if we lose one of the main path of the oscillation, we may also create some turn stability issue actually, because we may overload the other path in the case of our system. So that's not electromechanical oscillation, but that could lead indirectly to problem of transient stability. But otherwise, for the aspect of electromechanical oscillations, I think it can only make the problem worse in a way, because the oscillation, the electrical distance between the generator will only increase. And actually, I did it on a small line, not in the path, and on a small line in a way, in a matched region to be sure I was staying in a small perturbation region in a way.
Thanks. And how about some, I would really like to, maybe you did that, it just was not within the scope, and so the intermediate case between AC system and when you segment the system, but then you have the cases with both frequency control and one of the types of PODQ. What about only frequency? Did you check that case too?
For the segmented system?
Yeah,
yes.
Instead of frequency, but because that part would be like also part of the puzzle. Maybe there wasn't enough space. There was so much that you did.
Yeah, it was to simplify the.
So did you draw some conclusions from that, or?
Actually, the advantage of having the 2 controllers on different power is that it simplifies the observation of the results. And because when we look at 1 power injection, in the case with both systems, we know from where it comes from. But of course, I did the simulation with one supervised controller at a time, and on only one VSC at a time, or only one link. And actually, the result I had was the same as the 2 supervised controllers together. That's why I took the liberty to put them together to simplify the manuscript. And that's because the 2 actions are quite separated. Actually, they play on different phenomena using different action, different active injections. And that's why showing them both at the same time is still fine to see each one separately in a way.
Yeah, thanks. Makes sense. Like a question on robustness. So when you're designing your POD controller, you target the inter-area mode. And how about multiple? Because we have complicated networks, and then we have multiple modes, and maybe many of them will be poorly damped. Did you think about this aspect, like having a robust controller that would be able to damp simultaneously, let's say within a certain frequency range, or the controller that you're proposing is also has a positive effect on the modes of similar frequencies, or within the range where we need to damp and that were poorly damped?
So. So first, it's perfectly feasible to design a PODQ controller aiming at more than one oscillation. And so for one given system, for one given power flow, we may try to aim different local oscillations. But we are, of course, not as affected for each one that if we target only one. So that's why I focus on only one. And also that leads us to the issue of different power flows in a way where we will have different, the oscillation may change a bit, the modes may change a bit, and in this case, I think we may need to redesign the PODQ or to prepare a design for different power flow that will be adapted, but I stayed only one particular case with one particular power flow.
And this is maybe a conceptual challenge now. So we have an AC case, and then we have fully segmented DC case. Have you checked, or like, do we need to have full segmentation? Could we just replace? It would be really nice to see this intermediate case when you stop at some point to find the most optimal solution. I could perhaps give an example from, let's say, in table 4, when you have AC based case and DC segmented case, then you have a new mode. So something in between, like when you don't have both, let's say, two DC links, so with one of them, just to see if this is good enough for damping the dominant electromechanical oscillation. Did you?
I tried that, and actually for the interior oscillation, replacing one line doesn't improve anything. Because the generators are still here, they are still in the synchronous regions. And so the other path is still here in a way. And I think actually the oscillation passing by this path is even more, unless we have supplementary controller on the PODQ, of course. And so if we only see the impact of the DC link without supplementary controller, it may mainly worsen the situation. And it may worsen the situation for inter-area oscillation, but it may also worsen the situation for transstability, as shows the example of the Chinese example I took at the beginning, because without supplementary controller, the parallel AC line will have to take all of the variation of power in case of perturbation. So, and actually, that was what has been done in the Chinese example. They didn't replace AC line to DC, they added DC line, which is really similar, and they realized that at some point there was some issue. Also, I need to say that in the Chinese example, nearly all of the VDC line are with LCC, which are less controllable than a VSC link.
Thanks. And then you talk about transient stability and the effect of this strategy too. Then you mentioned that the transient stability in general was improved. Does this also apply for the segment in the segmented system where a disturbance occurs? So if there's some, let's say on figure 714A or 715A. So in the we're in this highly nonlinear segment. And then I would say for the first swing, actually, we have larger oscillation for the segmented case in the region where the disturbance occurs. Later on, we see the effect of the POD and that it performs better than the AC case. So this is one example. So 740A and 715A, and the same for the region 2, that would be 717B and 718B. So it's a similar, so perhaps it's worth of it. So it still works properly. I'm just thinking, have you, did you think about this?
Yes. In the control Cerrada system, the transient stability issue was between the two regions. So we had, in case of a fault, we had the potential overloading of the transmission line. So in the case where the AC transmission line are already quite stressed, so they have a big power flow in these lines, desegmentation will strongly increase the stability, the transient stability. However, indeed, in the, let's say for local perturbation, locally, we have less inertia and primary reserve, so we are more affected by the fault as a first overshoot. So I didn't investigate it as much as I would have liked, but yes, we may have issue for transstability. We may have some improvement on some aspect and some issue on some others.
Yeah. I've seen that you also have this in the future studies, so the
Yes.
effect of DC segmentation and transit, which is good to perhaps be investigated a bit further. So my wrap-up question. So let's say this is a mental experiment now. So we have you have continental Europe AC grid, and you have a lot of freedom to plan a strategy for DC segmentation. So what would Mathieu do first? And you have the financial support to do that.
I haven't studied this system as much, so with my own background, I will start with some small analysis that will tell me what will be the main interoscillations, and I will try to compute my algorithm to see how it would work. The issue is that it will certainly cut the system in two right in the middle, and actually right in the middle in Europe is in the region which is really meshed, with it's really densely populated, so maybe it will mean cutting way too many lines. And so maybe it won't be the good idea. So I think that in general, the TSO will always be able to say which are the lines that tends to be overloaded a lot, and that will be good candidates for desegmentation. It's more transferability than electromechanization, but it is. Another way to see it, so for electromechanization will be to ask again the TSO what are the regions that oscillate the most. We know that in Europe the Iberic Peninsula has an issue of oscillation against the other extremity of the grid, which is actually currently evolving. And so that's why the example of the Pyrenees is quite good, because it's one interconnection which already have a big share of DC, so less cost to do it. And it's one region when we see electromechanical oscillations. And so I think that in general, the boundaries of the country or the geographical boundaries will be a good place to do segmentation, because by historical reasons, they are the region with in general, they are the region with the lines that tend to be the more overloaded. We had a blackout in Italy, for example, so maybe upgrading all of the AC line from Italy to the rest of the system will be a good start for a good thing for transstability. So mainly mountains, actually.
Okay. Thank you, Mathieu. I enjoyed while reading your work and listening to your presentation. I'm very satisfied with the discussion, so I would just like to congratulate to you and your supervisors for the good work.
Thank you very much.
Right.
Okay. Thank you very much. We will continue with Professor Beerten.
Thank you, Theo. Thank you also from my side, and also your supervisors for the nice piece of work, well-written text, very clear presentation you also gave today. I think the idea you present in the thesis is very interesting. It's a bit out of the box, and it goes a bit against conventional power system thinking and the way we've been moving the power system, which is nice. I also think that the idea that you presented to use this concept of dominant oscillation paths is a very interesting one, and I think it can also have other applications as well. But I'm here to ask questions, so let's go. So I have a couple of general questions, also some that are a bit more detailed. I'll start with some general questions first, and go a bit more in detail, and then end with some general questions. Now, historically, HVDC and DC segmentations actually has been around for some decades. But when I read things about it in the 70s, from papers in the 70s, it was being put forward as a means to reduce short-circuit currents. Now, interestingly, it's an aspect I didn't hear you stress, that it could be a potential advantage, but that's what authors some decades ago saw as the biggest advantage, because they saw a risk of short-circuit currents getting too high in the AC systems. The 70s is when everything was being meshed, when a lot of generation plants were built. Do you think this is an issue, or could be an issue still in current day power systems, or not so much?
It is still an issue for mainly small power systems, and it will depend a lot on the control of the DC link. And so for grid following is not as good, but grid forming can also strongly increase the issue of short-circuit current. And so that's something that could be added.
Well, I think as long as it's converter, I don't fully agree with the point from grid forming, because as long as it's converter based, you'll be limited with nominal current. It's just if you have a lot of converters, then we don't really.
Yeah.
And then how much do you expect these oscillation paths to change? Over the decades. Or over the years, because the idea you present is to cut off some AC lines, replace them with DC lines, but that means that this has to be a critical path all of the time. Do you think this is an issue or not?
So the question of the variability of the path and the oscillation is very important in the case of the segmentation, because it's a permanent measure, as you said. We have different aspects. So currently, the main inter-oscillation mode, they evolve depending on the power flow, but they stay more or less the same, and we have the main one that at least come back quite often. And so trying to stop them is a good thing for the short term, that's for sure. Now for the long term, actually, it will depend a lot on the main geography of the grid will not change. I mean, if we don't add a lot of new regions, the main geography of the grid won't change so much, because the center of population are the same. So I don't think that the main interior mode will be. I mean, they will change a bit, of course, but I don't think they will be completely transformed. And but anyway, the main thing about the tool I provide, it's just one more help for the planner in the planning phase for one aspect of the grid, but of course it must not overlook all of the other one.
Well, I think you're right in assuming that the architecture of the system will not change that much from AC lines perspective, because those are the ones you need for your how to propagate the issue, because we cannot build the lines easily anymore. I'm not too sure about the generation pattern though, with phase out of nuclear in some countries. I mean, cities will stay where they are. The question is whether generation will stay where it is, and what kind of generation that would be, and how that would feed into what inter-area modes become. So I think that's a potential challenge to apply it in a real system context, is that, well, it's a drastic move, and the future is uncertain, but an interesting move, nevertheless. You also said, I was a bit surprised, you said it's not to be mixed with operational control measures, but why not? Because I think if you have those links available, you could think of an AC system that's reconfigurable. Could be an interesting control measure to improve stability in the system.
The action to do this segmentation is not it's a planning action. So to switch AC line to DC, or to add new DC line, whatever, that's a planning action. And it's not like we change the control of something, or we disconnect an AC line for a short duration like we do in the international ice landing. It's the planning action. However, as you said, it will be really useful, and it will it bring more controllability. So it could be used for the operation, and it brings a lot of possibility for the operation through the controller of the link. So this segmentation, the action to do it is a planning action, but it will strongly affect the system. So it will also strongly affect the operation of the system by transforming the system completely, and by bringing new controllability to the system.
Yeah, because also the example you gave from China, I think, is clearly pointing in that direction. I mean, they built massive HVDC links going all the way from the west to the east, and then decided to cut up the AC system as a result. They just had HVDC reinforcement of the system. We might need similar things with all the offshore wind coming in. And then those links were there, and you could argue that, this is one way of operating the system, just to segment it if needed.
And also there is a question of non-permanent segmentation in a way. So if we have the parallel AC and DC line, we could potentially, from time to time, disconnect the AC line. So that will be an operational action that will get to the segmentation. So in this way, it could be an operational action indeed. I studied a bit and I found mainly disadvantages because the idea is that in a case of a perturbation, we may want to disconnect the AC line in parallel of the DC link for some reasons. But I don't see cases where, I mean, in most of the perturbation, disconnecting one of the AC line will make the problem worse. So the main example is for transstability. So if we have a big power imbalance between two regions, we may have a loss of synchronism between the two regions. And so we will have to disconnect the AC line. And that's what's called international sonic or not international, depending on the case. And but that's something we already do. And it's disconnecting the AC line is a last. It's a last minute, not last minute, but it's really the last thing we'll do because it will create even more perturbation. So having this idea that we may use the DC link to have desegmentation, but only on some cases, it's already done in a way, international Icelanding, and it won't bring much advantage, I think. And I can say it's already done because in the last event of in January 2024, I think we had a disconnection of a power system separation of the continental European grid between the east and the west of the European continental grid, and we had the DC link between Italy to, I think, Greece that stayed connected. So in a way, it was this segmentation because this link continued to operate between the two asynchronous region, and but that's something we'll redo in a way, and I will call that international Icelanding with parallel DC link that continue to operate in a way.
Yeah, and also a region in the world where they are advocating that the DC is helping them heavily in that regard is the US, where they still have a cut-up AC system connected with DC links, and avoiding propagations from one area to the other is also one of the reasons they advocate for keeping it that way. Maybe going a bit more into some detailed questions I had on the modeling on chapter 3. So in the beginning you mentioned that MMCs can sometimes yes and sometimes not be modeled as two levels. I think discussion on that is a bit more, well, if you want to do it fully, it's more than what is in the thesis, but there I'm wondering, is it really important for your intended use whether you can model it as a two-level or not?
No. We used the most detailed. Actually, we had this model available in the company, Supervised Institute, and as it didn't bring any issue with the computational time, we say that it's easier, it's better to have more detailed system that are safer than to create ourselves simpler one where we may have issue when we create them, and then we won't have better results. So it was more a question of saving time and being safe in a way, because my PhD didn't focus so much on modelization.
Yeah, I agree. It's a good way forward. I think only if you would like to look into converter misoperation, fault right root properties, and so on, and as how that could kind of play a role in how large-scale events develop, then then those details might be important. But that brings me to another question I had on the modeling. If I understood correctly, your AC side model is completely phasor based. For the DC side model, I would describe it as some simplified electromagnetic transient model, because you can take line dynamics into account. I'm wondering why you're having an electromagnetic transient model at the DC side. Would it not have worked with just a power injection model? Just saying, here is a power I take, with assuming reactive power control at the both station, and I neglect the losses?
Actually, neglecting the losses won't change much because they are really small, and we take into account only the losses of the DC line, not of the VSC in my model. So yes, neglecting the losses will barely change anything. And yes, actually, with the level of detail of my research, I think we could have simplified also the DC link with only power injection. It won't have changed.
That would also be my initial guess, of course, to be checked and for all the scenarios.
It's the same thing. We use what we had available, and we can do more. We can do.
Yeah. On the when you started to introduce the idea of DC segmentations, you stressed at several points in the thesis that you removed the PSS to really get those poorly damped modes. So am I correct that you did this for the 6th generator test system? Because and also for the Nordic test system, I was wondering what changes you made for the 6th generator test system.
I did only for the conductor area test system.
Only for the conductor area system.
For the other one, I kept. I did some try, but not in the manuscript.
Because that brought me to a reflection. How much could you, let's say, do about those modes by having better tuning for your PSSs?
I didn't study the tuning of the PSS or the other way to damp power oscillations. But the thing that with desegmentation we go even further. That's the idea. So that's why I didn't go into more details, and I stayed in the focus of segmentation because there is really little study on that, while there is so much study on PSS. And so I think that desegmentation is one solution to stop the interference oscillation. There is many other ones, but the difference that desegmentation, it structurally suppresses the oscillation between the two regions.
But of course, it makes the results. I mean, if you would let's say make them as damped as you can, then they may not be as bad as when you don't really damp them to show the differences.
I think that cost-wise, segmentation doesn't compete at all with the other solution. We have to damp interference oscillation. That's for sure. And just it's giving one more argument to do it. But of course, we like to say that currently, as far as I know, it has never happened that we built a DC link for power system stability reasons. We do it to increase power exchange capacity between the region. Power system stability, so the addition of the gain of power system stability is one additional advantage.
And maybe going a bit further on the discussion that you had with Marina on the on kind of an intermediate solution where you would keep some AC lines in. There, I was wondering if you think about the algorithm that you propose in chapter 5. Right now, you say, okay, I define my edges, I find the most critical path, and that's the one. And then you also move forward in the chapter 6 in terms of segmentation. You say, okay, I cut up that path. Next. So I was wondering if you could think of changing the algorithm, that you would rather than going one by the other with the idea have to cut it up, that you would say I'm going to rank them kind of as to how important the AC links are, to kind of give a priority as to where you might want to disconnect things.
It will be really hard to do. I think, it will give us really a lot of potential path, which will be really similar to one another, actually. By just, I don't know how we could say the algorithm to change a bit, but anyway, we could do not an infinity, but really dozens, even for the NIC 44 the same. We could do dozens of paths that will respect the rule of electromechanical oscillation path with just changing one bus, for example, in one region. And so it's definitely feasible. Even right now I cannot think of how to do it, but it's definitely feasible. And so by cutting one, I'm sure I will find another one which is quite different. Because if we look at the map, if I can find it easily, it's not too far, there it is. Here, they already have some buses in common. And by saying the algorithm that you cannot go here anymore, this line doesn't exist anymore, I guarantee that it will go a perfectly different path. And if I try to have every single path here, maybe I will go first to this bus and then back here, and so it will be a really similar path, and that won't bring much value. And so what interests me is the different lines that can be reached in the center of the path, in a way, next to the pivot bus. And by suppressing one, I'm guaranteed I will find another one.
Yeah.
But of course, there could be a lot of small improvement or small variation of the algorithm.
Yeah, and then on the maybe going to the chapter on the control, yeah, you already discussed it a bit as to why you went for reactive power there in your POD design. You said you wanted to avoid that it could interact with the frequency control, that it could propagate perturbations. But I think the main issue is, yeah, I was wondering there if it's really a propagation of perturbation that is really the challenge there. I mean, what you essentially want to avoid is that you start coupling them again. So I don't think it's really okay. You do something at one side, it is reflected on the other side, but there it comes across as kind of a forced oscillation in the power system, assuming it doesn't interact with the modes in the system. But it could be that you start pushing the system there on a mode that it has. So I think then it's more, I mean, that's my thinking on it. I think it more than would depend on the on having intra-area modes that would be similar in the two regions that you kind of got.
Yes, so my first fear about doing PODP was that I will recreate the oscillation by doing the PODP, the same inter-area oscillation I'm speaking.
Why would that be the case?
But that's not the case, because that's not the case, because as you say, we are not working in the mode, and mainly we play on frequency and not angle difference. If we play on angle difference, we may recreate the mode, of course. But yes, there is. Actually, I didn't think about this particular case. But when I speak about perturbation, it's a really general way to say it. And so one example I didn't think about was maybe that if we have two oscillations, local oscillation with a similar frequency, they may stimulate each other in a way, resonate against each other maybe. And so that could be an issue. But I think that's similar to an inter-area mode maybe. Because if two local modes are the same frequency, I guess that in the AC system they may have been.
I don't fully agree. I guess it depends. If you somehow building coupling mechanisms in your control that would couple those modes, then yes. But if you do it on one side, then the other side, I think by definition would not be coupled. It would just mirror the effect, but it wouldn't interact with the system there. So then it's more of an issue as to whether, you're pushing the power system or exciting it at the wrong frequency, essentially, I think. So I think it's a bit more nuanced than that. So I think it can work, but there are things to be careful for. But the same applies into the voltage control that also needs further investigation. yeah, on the idea of using the center of inertia frequency, I found it an interesting concept. How do you, what do you think it's practically doable to determine it, or what would be needed to put it into practice?
So we need to measure with PMUs the phase of each generator, and we need to have the relative inertia of each generators, and then we need to send this measurement in real time, and so that means we need really a lot of measurement devices, which is expensive. We need to have communications on between many PMUs and the VSC, so that's a lot of electronics to be added. And with all of this communication, we may have some communication latency. In the manuscript, I have an example with the communication latency taking into account, but it's quite a simple case of communication latency where I consider that all of the information arrive with a small delay, but with the same delay, because if they arrive with different delay, maybe even different. And so the result I have is that without the delay, PUDQ with the frequency of center of inertia is slightly better than the one with local frequency. And with a simple delay, it's become not as good with still similar result. And so with more delays, with different delays between the PMUs, it gets worse a bit. And anyway, it's look like really it's really a lot of things needed for a really similar result than the one with local frequency. So I don't know why we should change.
Going maybe a bit again then back to the general question, so then we're approaching the end of the questions I will ask, not that I have, but that I will ask. We already reflected a bit on this potential coupling. You mentioned it as a point for future work, but I think that the elephant in the room is really grid forming. And when you add that to the link, and let's do what's with that. Because right now the story is HVDC is going to solve everything. But I would like you to reflect a bit on what it would mean if we get grid forming in the system. Let's start with the HVDC link, but maybe also reflect on what it would mean if we get it in other converters in the system. So if we start with the HVDC link, do you see any risks for grid forming? I see some risks, so I'd like to hear your opinion.
But the risk of grid forming is always the synchronism with the rest of the generators, and but I have to admit I didn't.
Well, the thing is, your converter is going to behave a bit like a generator, kind of, and I think it then depends on what the other side of the link does. If it starts, if it acts a bit like a generator, and your other side of the link does as well.
It would recouple in a way.
These schemes with dual grid forming are being introduced, so they behave like generators at the two ends. A generator can potentially, depending on the settings you give it,
oscillate again.
Oscillate with the rest, with respect to the rest of the power system. So I'm not sure that if you add grid forming to the picture, that you would still have the same firewalling effect. That further investigation is needed, but that would be my main concern.
Yes, the main issue that we will have some active power injection, so we need to investigate how it will propagate the faults or oscillations.
And the reason why I brought in grid forming for the rest of the power system is that converters are everywhere. And we already discussed in the beginning that you said, okay, it's plausible to assume the AC network is not changing. I agree, because we cannot build lines, but we can build converters. And then we want them to have grid forming, and maybe also in a medium voltage system or on industrial sites or everywhere if we can. So that means that all of a sudden you might go to a power system where the generator side changes quite a bit. So what does that mean, and for the future of your inter-area modes and for how they?
For the inter-area mode, once we have done the segmentation, it doesn't matter anymore.
But you might have gone for a DC segmentation.
Sorry?
You might have gone for a DC segmentation, which after 10 years prove not to be the point of concern anymore because of grid forming, and you can steer where the generators with synchronizing properties
I think that so having a lot of grid forming converters because they are not placed at the same place than the conventional electricity power generation, that will indeed change the architecture of the placement of the generators, let's say. And so that will necessarily change the oscillations, interior, locals, and whatever, all of the oscillations. But the advantage of segmentation is that, okay, I may not have stopped. Okay, if we had not done the segmentation, we may have interior oscillation, which is really different, and that will require interior oscillation that are really different, and that will require a different segmentation. But at least I will have separated some of the generators, and they, even if they were not existed before, I have separated them, and they cannot oscillate against each other. So even if the interior oscillation is not the same, I will stop some of them. So with this example, all the generators south and Norway won't oscillate against the other generators, whatever happens, even if they changed. So we'll have, again, for interior oscillations, some of them won't be able to appear in a way, but maybe it will not have been the best for the new oscillations.
You did good in defending it. I also had a question, a bit provocative, but it was already asked by Marina. Where would you put up the European power system? But we will not go there. But the very last question that I had, which is also reflecting a bit on prior discussion you had. So if I'm playing the devil's advocate here, an AC system has been being put forward as let's interconnect more countries, and we want this one power system to become stronger and stronger. Of course, that also aligns well with political goals. So I mean, I'm playing a bit devil's advocate here. I would like to hear your opinion, but it could feel a bit like a political time bomb in a way, what you're proposing, because you already indicated it. Where would you cut up the power system? Well, where there are not too many paths, that's on the borders. So rather than reinforcing the power system, it might come across as let's just cut it up and then connect it in a way that we can quickly switch it on, off with more controllability. So it could also be used or seen by politicians in the future as going completely against their ideological view of what society should be or what Europe should be. I mean, they don't care about the power system, but how would you convince them?
First, maybe some of them will change their mind, and we see on the political side that some politicians are much more protective, and they are going away from the European Union. So maybe that will be, I would not like that, but maybe that will be the motivation to do this segmentation.
But then you don't need to build the DC links in the first place, right?
No, because it brings power exchange capacity with more control. And actually, it's the same thing as improving market operation. I mean, I'm really not into so aware about market operations, but I found actually a patent on improving market operation with segmentation, and basically what they say that we need to do the segmentation along the market boundaries, and so it's I want to control more what power is sent to the other countries and what I receive. So it's a bit protective in a way. And so in the political aspect, of course, it's not going in the way of the European Union. And so I will convince them by saying that, not myself, but one way to convince them is that you gain controllability, but mainly by going from AC link to DC link, you increase power exchange capacity. And that's what we are doing. We are building new DC link between France and Spain, and many other ones have been built recently or are in building or in study phase. And so upgrading one AC link to DC is increased power exchange capacity. And it may also lead, in some cases, to desegmentation.
yeah, well, gaining controllability, to put that to a politician might be something that they like to hear, but I'm not sure we want to put it to every politician. But another argument could be that, well, it's what you're already doing, by the way. It's just the logical next step, because it seems like the only thing we can build on country borders often are DC links
Yes.
more and more. Okay, thank you, Mathieu.
Thank you very much.
Also for the nice discussion, and congratulations with your work.
Thank you very much.
Thank you. Very interesting discussion so far. It's good to listen to it. We will continue with the discussion then with Dr. Maider Santos.
Hi, Matthew. Good morning, everybody. First of all, thank you to the PhD student for small time, and to the directors for the invitation, and for a really well-written document, because I normally read a lot of documents, and I was like losing my conviction. Now I see that they are students that are able to write well. The document is well structured and coherent, so thank you for the document. I have learned a lot, because I've been working a lot of time in grid codes, power system, but not very expertise of PODs. So maybe my focus or my point of view is a little bit different. I had 3 general questions that they have already been very well answered. So I think that maybe I will go for minor things more related to my background. I think that there has to be always questions and buts. So my great but is that you have many work done, many results, and the state of the art is very well. But in my opinion, the graphs and the results should have been better explained. You have so many graphs, and maybe there are 6 or 10 graphs with just one paragraph that is saying we have obtained this, and you can see this, but you're not discussing it like in here. So it's a little bit speechy, because I think that you could have better sold your work. It's not bad. I mean, it's not like, oh my God. But when you are reading and you are not an expert, you really appreciate that kind of explanation. Or rather than saying we have increased the performance by 2%, why? For example, with the CCT, when you say we had improved the CCT up to above 2 seconds, why? Due to the segmentation itself, due to the size of the bus. So that kind of why happens the things is my minor part, okay? In that sense, for example, when you mention the power stability issues, you mentioned that historically we have 3 of them: rotor angle, frequency, voltage, and that there are 2 new ones regarding converters.
Yes.
For me, it's a little strange that you didn't just mention which kind, because you are using converters. So could you just explain a couple of lines or with a couple of examples when you are talking about that 2 new power stability issues? What do you have in mind, or what is the explanation, or what kind of problem issues do you find there?
So we have the power stability associated to the new the DC converters, and so we may have for line commuted converter we may have issue of the commutation fault, and for the VSC we may have internal fault to the VSC, and mainly we have the interaction between the DC converter and the rest of the grid, and the DC converter between each other. And so we have, for example, the POD action that could interact with the existing oscillation, and so that's one tool, but that's also something that that can be an issue in the system.
I mention this because it's a little bit strange that, of course, you have to choose a main topic that is frequency stability, and it's perfect. But when you introduce concepts and you don't explain them, it's like I think that you need to justify it. Just justify. It's not wrong, but it was like you mentioned two new things and they are not explained. So for me, it was like, oh, I wasn't aware. I was aware of resonance problems or whatever, but I wasn't aware that that power system stability scheme that is like forever was changing. So for me, it was, oh, how interesting is this? And suddenly, oh, what does? So just that kind of comments. Another thing that for me was very interesting, apart from the COE of the COI, was the concept of perfect size power system grid or whatever that Marina also mentioned. Do you think that could be interesting to develop an algorithm regard to that perfect size in mind? Because I didn't read the paper. I don't know if they, for establish that perfect size, they establish some parameters. They define some set of parameters, an algorithm. It's something that could be interesting, maybe not for inter-area oscillation, because I think that the focus is different, but something that could be interesting to have in mind if you want to segmentate the whatever, the AC grid. Another, I mean, a little bit out of the box. Could be interesting that to keep in mind that perfect size in order to another criteria to segmentate the ACD grid.
So so of course it's a balance between different stability issues. The bigger the system is, the better it is on the aspect of frequency stability, because we have bigger total inertia and bigger primary response and so on. And so for frequency stability, the bigger system is better, and that's why that was the main issue in the past decade, and that's why we made bigger and bigger system. And for some islands, we still have issue of frequency stability that are quite common for smaller systems that could be islands or smaller countries, smaller grids, and so in this case, it's still an issue. However, for a big system, we have different issues that arise. In my case, I study the inter-area oscillation that can be an issue. It's not really the size of the system that is an issue, it's more the architecture. It's if we have some bottlenecks in the system, and that would be, for small signal stability, is having groups of generator coherent to one another, coherent group generator, different coherent groups of generators that are a bit far away. Electrically speaking, that would be an issue for electromechanical oscillations. For current stability, again, it's more the architecture. It's if we have bottleneck in the system, so region with less lines, or if we have an imbalance between the production and the consumption. So it's not really, I mean, it's issues that arise with the size of the system, but it's not directly linked to the size of the system. In this paper, they speak about blackouts, and cascading outages. So if we have a bigger system, we have much more chance of losing a line, of any kind of perturbation occur much more often, of course. And then once we have a perturbation, it can always propagate, and they study so the cascading outages is that is one line is disconnected for any reasons, and so the one parallel line is overloaded and get disconnected, and because of that the parallel line gets even more overloaded and so on, and that creates cascading outages. In a small system, the outages cannot be bigger than the system, of course. For any system size, it cannot be bigger than the system. And so that means that for huge system, we create the risk of a system-wide blackout. And so what this study show is that the bigger the system, the bigger the chance is having a huge blackout. And it's maybe better to have two small systems independent of one another, that each may have small and medium-sized blackout and not having huge size blackout. And that's linked together with the last research on blackout reduction with this segmentation, is that big blackouts are suppressed nearly.
Okay, so if I understand correctly, it depends more, for example, in the strength of the grid, the inertia, whatever topology that may be that even if the size is important, the behavior of the whole system is the more important thing.
Yes.
When we talk about that perfect size. Okay, very, very interesting. One thing that for me was like quite difficult to see, or in this case I missed, was whenever you talk, or at least whenever I talk about reactive power control, to my mind comes the voltage, always. Well, when I work in distribution grids, not, but normally. So for me, it's quite strange that you didn't mention anything about the voltage at that nodes. Even you didn't mention anything about power factor, or for example, in one result you saw huge amount of megavoltampere reactive. So if we have a line of AC line rated at 1 megawatt and megavia, and we want to replace it with a DC line with your controller, 1 megavia will be enough, or due to the high amount of reactive power that you need to that the DC link, that converter, be overrated. Maybe this question is silly, but was like, for me, it's like, okay, that DC link should be overrated in order to be able to maintain the total active power, and also to be able to, for me, 300 megawatts reactive megawatt, however it's called in English, is a huge amount of power. And also regarding power factor, I mean, I know that it's not the focus of your work, which is very good, but grid codes and power factor and voltage oscillations and dips is very important. So for me, it's like, have you keep in mind all those voltage issues that could appear for injecting reactive at one point, reactive power at one point?
For the impact of voltage, so of course, any injection, any action on reactive power has an impact on voltage, naturally. And so that's also why we need to limit the action on reactive power. And so we didn't observe problematic variation of voltage power in our studies. And and we didn't focus too much on them because the issue didn't appear, and it wasn't the initial focus. And then for the rating, you saw really a huge injection of reactive power. And that's because the PODQ are not placed perfectly for the system. What happened is that if you want to dump an oscillation with facts, we'll place the facts in the best position possible. And in our case, we place the VSC with having in mind the interior oscillation and not the local oscillations. And that's why we had to limit ourselves in Q and reactive power injection, because if we are not done so, we'll have even bigger reactive power injection. So that shows that the placement is not perfect, and so we limited ourselves with reactive power to avoid issue, and one of them could have become the voltage of the system.
Yes, I really had that question because you can see that the reactive power is saturated at some point, and I said, this is why they found a voltage issue. Why is the control saturated? So with this explanation, is clear now. Just to note, you have a PODQ control. Does it work in any kind of grid? I mean, for example, normally you in the high voltage you look to have the power active and reactive power decoupled. And now, when you introduce that, at my point of view, that PODQ, you are coupling for reactive and active power. So if the grid is very sensitive or is already coupled, I think that there could be a problem with the PODQ. If you go to system where the the active and reactive power are coupled with coupling, I think that you could find a problem there. But it's just because I don't know if this PODQ concept can be taken and a low voltage systems, different lines, or is there is an restriction that should be used in medium and high voltage grids?
I'm not sure. I think there will be, but
Okay.
I have to admit
Okay. No,
I didn't focus on low
okay.
voltage.
You don't have to know everything. Nor do I. I mean. Okay. So I think that I have just two more comments. Regarding the linearization process, did you do it by hand? Did you use, because you have the Modelica system, and how to obtain the linearized model of the Modelica system? Because I know that it's a very complex thing to do by hand, and was just if you use a...
So you mean the... that's better. So you mean the...
MATLAB model?
This one?
Yes, that
yes.
model.
So I did two different kinds of linearization in my study. I did one with Daimola, that is a numerical linearization from the system we had. And that gave us some results that we study and that I shown you in the small scene analysis come from Daimola. And then for the algorithm, we needed more detailed small scene analysis. And so that's why we decided to use with SSST. And the difference between these two linearization is when they are done. So for Daimola, it's numerical linearization that is done fully by the tool. And for SSST, it's before the tool, is that we need, by hand in a way, to have the linear model of the system. So for the conductor system, I already had them available, and for the Nordic 44 system, I had to create the linearized model. So in a way, SSST give us exact results, but the simplification is done beforehand, and Daimola do the numerical linearization. So we compare the results, and they are not exactly the same, but that always happens with linearization.
Okay,
But they are still similar enough.
My question is, wouldn't it have better to use, for example, Power Factory, that with just one model you have everything? I mean, you introduce because if you change your operation point, you don't have to reduce the. I mean, normally we use Power Factory, and they already you have the model, and you don't need to linearize the model. But I mean, it's just a comment. It's
Yes.
not. And the last one, when you comment one of your contributions, that is that the use of the COE frequency. In which context do you think that could be interesting to use it? Do you think that would be a context where the difference between the local POD and the global POD could be more than the one that appears here? Because I mean that from outside it seems that should be better, but then you saw the results and it's not better. So do you think that is due to the system itself? I mean, the Nordic 44, and that could be interesting in another kind of power system or with other kind of inter-area oscillations. I don't know.
So that may depend on the system. Of course, we are surprised the difference was so small. But I'm not really sure how the system will affect the difference.
You did expect better results?
Yes.
Okay.
It's not at least without the delays, we expected better results. But we are surprised a bit. Okay. And also I know that some study to simplify a bit, they take only a few generators, representative generators, to have an approximation of center of inertia. But so there is a lot of different ways to do, and I don't really know why the difference is so small in our case.
Okay. that's all for my part. Yeah. Thank you.
Thank you.
Yeah, thank you very much. Now we go to Professor Sigrist. Interesting discussion.
First of all, thanks a lot for inviting me. To you too, thanks a lot. It was a real pleasure reading the document and listening to your presentation and to the discussion. I followed up
Lukas.
clearly because I also had to check what I wanted to ask you, but it really was a pleasure to see how you interact and the things you asked. And yeah, I think we could go on like this, but I'm not sure if everybody agrees. Many things have been said about the document is well written, it's well structured, it's very clear. It's very clear and easy to read, so you clearly state the problems, the one you want to solve, you clearly state the contributions that you solve it. There are always open questions, that's not the point. The presentation was very clear, so from that point of view, you did a great job. Well done. Congratulations. And also, of course, congratulations to your two supervisors present here, and Juan Carlos, I guess he's online. Congratulations too. Well done. I have still some questions left. Even many have addressed them, but I have still some curiosities. So one is related to points raised by Marina and Jef about, is it planning, is it operation, but in planning, what are we actually doing in planning? So I think in planning we have to differentiate between a thing which is we add new links to a system. That's one thing where you add a lot of capacity, and you substitute existing AC links by DC links, which add some capacity. But then, of course, you have to be careful because the planning is always about where do I have to reinforce the grid? And you usually have to reinforce to transmit more power, not less. So the question is related to all this discussion, and it seems you will have to do a PhD in economics too. And it goes like this. You identified oscillation paths, and then related to these, you have your DC segmentation proposal. But I wanted to know whether you're aware, for instance, in the Nordic system, we can also discuss later, of course, how much do these paths align with the economic paths, where they want to reinforce the grid? So do these two concepts of oscillation path, and I will call it now economic path, are they aligned? Are you aware of that? So it's a very open question, of course.
That will depend strongly on the system. And I said for the example of the European system, the place where we want to add links is mainly at the natural boundaries, because that's where we made less. We saw a lot of new construction between in the Pyrenees, in the Alps, and with the asynchronous region, but that's another question. Let's speak about only the continental region. And so the economical one is about places that lack power exchange capacity. So it's places that have transient stability issue. And the one with interior oscillations, it will be, if we take the bigger interior oscillations, it will be more or less in the middle of the system. So that will depend on the system. If we have one region, imagine just two countries linked together by only a few AC lines, then it will perfectly coincide, of course. I mean, nearly perfectly coincide. In the Nordic countries, for example, it's coincide to a place where we have little lines, but they are quite powerful already, so I'm not sure they need so much. Actually, I know that the one from north to south needs some reinforcement because most of the production is on the north in Norway, most of the consumption is the south. So that's one path, let's say, one direction that need reinforcement, and that should continue with the creation of a new offshore wind farm. So I think it really depends. It's case by case. Some cases it will align really well, and in some cases it may not align at all.
So you're basically saying for reinforcement, you would say the bidding zones boundary, right? That's what you refer by the natural boundaries, so market bidding zones. To reinforce, but the inter-area oscillation is rather somewhere in the middle, like if you use your picture. So this gives rise to another two questions. So if we talk about the bidding zones, then for increasing these transboundary capacity, is it really needed a DC link or is an AC link enough?
The question is, I mean, about power-wise, it's the same. I mean, we may need to make a few more AC line than DC line. But what we observe is that in the last years in Europe, most new interconnection between countries are all DC, or I mean, I'm aware nearly of DC ones. They are most of them DC, and that's not because of a power capacity issue. It's more because of geographical constraint and sociological constraint, that people don't want new overall lines, and people don't want new overall lines, so it's better to build underground or underwater in some cases. That's more for geographical reasons. And when we do cables, the distance at which DC is cheaper than AC is much shorter. And that's for the same reason that they do the alternate project currently, that they need to increase the projection between north and south of Germany, and people refuse to have new overhead lines. So they could even create new underground cables or upgrade AC line to DC. And for some economical reason I don't know so much about, they decided to do an upgrading of AC line.
That's where I was heading to, and I was looking for that answer. The other question comes, okay, for new capacity we prefer underground. So you will see that's usually the DC option standard choice. But then if you say, well, if you really want to segment the DC, you have to disconnect or to change the whole AC infrastructure. What do you think a regulator or the society would think about if we have to pay all these changes? Because if you want to DC segment the Iberian Peninsula from the French system, you have still to disconnect 2 AC links at least, to 220, and then you have other links too, 400. So you have to do something with them. It costs. Well, if you disconnect them, then you lose power transfer capacity you don't want. If you want to upgrade them, it costs an extra money. Any thoughts on this? And then I go rather into the thesis.
I mean, it costs money to upgrade them to DC, but it brings new capacity, not as much as new DC link. So maybe it's not as much cost efficient as new DC link, but it has some advantages. Otherwise, they won't do it in Germany currently. And anyway, we are adding capacity. So that may happen anyway. And then surprises AEC line, maybe we can go back to more political things, and maybe the reasons could be for a new national, a new protected area, and it will be a good excuse to suppress, and people won't be happy. People will be happy if we suppress some other lines in general. Will be a loss for the electoral grid, but in general, people will be happy.
And we'll see then if we talk about money, they also that happy. But yes, if we talk about the money, then because it adds extra money. Okay. Good. So, as I said, it will require, I guess, another PhD. In engineering, it's not possible anymore, but you can do it in energy economics. You can go
think about it
if you want to. So the second sub-question is related already rather to the grid or to your thesis, because I think you very well illustrated how the oscillation path and the segmentation works. So we had this small scale system, then the Norfolk one, Nordic system, which is larger. The result, we can follow them as humans because you have these weak links in between the two areas. You could say, yes, that makes very much sense. Now the question goes, because you said, well, the Ontario oscillation, I would split it in the middle. Seems reasonable. What would you do in the north-south oscillation in Europe? Italy against north of Europe, which is fully meshed. I know Switzerland has how many lines in between? You really want to substitute all of them? And the French, Italian border, French, Austrian, French, Slovenian, all of them need to be. How? The question goes, how would your algorithm do? Would it just go on like this, or maybe what Marina suggested, or Jef, some intermediate solution, not splitting completely?
So,
so how does your would your algorithm works in a very meshed system? How do you see it and the applicability?
Currently, the algorithm as it is now will find the lines and cut them right in the middle of the path. So, as you say, it will be really a lot of lines, and that will definitely not be a realistic solution in the case of the north-south oscillation. A slightly more realistic solution is to segment a bit more on the side of the path, and so around the, I guess the place with the less line will be around the Alps. It's still a lot, but it will already be way less, and a couple of them are already DC. And so that will be not as good solution in the aspect of desegmentation because it won't so well limit this interior oscillation, but it will still play a role. And it's also goes together with the canonical aspect that it's region that where we want to increase the power exchange capability. And I'm forgetting one point.
So essentially you would, let's say, the optimal solution would be somewhere in the middle, whatever then the middle is in such a large system, where you would say, well, that would deviate from them because it's not practical.
Yes.
So could you imagine that your algorithm could be coupled with some other indicators to take a solution that is globally more convenient? I'm not sure how to express it. Say economical ones or number of lines or...
economical one can be really simplified by the number of lines plus their power exchange capability. That's more or less because the price of the VSC depends nearly fully on the power, on its capacity. So we could need to add two criteria. One is accepting to segment not as much in the middle, or far not in the middle will be really hard to implement. And the second one, which will be quite easier actually to implement, is the total cost of the segmentation, and it will be the number of lines plus multiplied by the capacity. So the issue will be finding this not optimal solution on the point of view of interior oscillation. That will be quite hard to find, but once we have them, and we have a few of them, compare them in the cost aspect in a really simple manner will be quite easy actually.
Okay. Yeah, because I understand that if you look at it from a planning or longer term perspective, of course you need to weight your decisions, your purely technical one, with other factors in the decision making process. Okay, so this brings me to another question then. Where do I have it? Yes, it has to do with, you mentioned it now with word, I think you used the word optimal or better. You used it also in the document on when you compared the dominant path with a random one. You used the word better, best. But I'm just wondering, what do you refer by better? So what is your measurement that any other random path is better, worse than the dominant one?
That was subject to a lot of discussion during the PhD, and we didn't matter to have a clear answer. We we didn't got a clear answer. Is that how do we define electromechanical oscillation path? We have defined it quite well. I mean,
Yes.
the first definition is not from ourselves, it's from the literature, is that we need to have the variation of a phase of observative vector of the bus frequency. And then to define which one is a dominant one, it's quite harder. And one way to measure it is by the observative vector of the branch current. So how much of the oscillation is passing by each line, so by each path. And so one way to compare them is to compare the different paths, to check in each path which one, to look for each path what is the line with the bigger magnitude of branch current of the defector, and that will be one criteria. But this criteria, when we have a model like that, is not so good because it depends of how detailed we made the model. If we go into more details, then two lines that are aggregated in our model, they won't be aggregated anymore. And so this path will be divided in two, and we'll have a much lower branch current of the vector. So for a simplification of the system, it's really hard to define that. And so the path will be aggregated path, main path. So the definition of dominant path, I don't think it can be given clearly, actually. So we can compare two paths with some criteria, mainly the branch current obscenity vector along this path or at the highest point of the path, but that's it.
Yeah. So what I get is that if you have a system clearly defined, clearly described by a model, then the dominant path can be defined. If these, of course, the system is a result of a model order reduction, then you're kind of in a fuzzy area. And that, well, what you compared is in the other arbitrary solutions, how close you are to the dominant, what you call the dominant. So I understand it in that sense, that is what you consider good or bad. But of course, when I read it, it was like, well, the oscillations through these paths are more observable or less, or the prices or the cost. So that was my question, but what does good or bad mean? So now I understand it's closeliness to your dominant definition. Okay, it's fair enough. It's fair enough. Okay. And then I have more questions, but I think I'll stick with one, and I will take a follow-up from Jeff's question on the grid former and the impact, but I will not ask on the impact. I will ask if it had an impact. So once you split the system and you set up the grid former, imagine it impacts. How would this affect your whole methodology? Because now you do it in like a two-step approach. You identify the path and you split. Well, now if you split and add the grid former, you join them together. You have again the path. So how would you do? It's an open question. I couldn't expect a final answer. I guess we had other theses on this.
If the DC link recreates the path, then I don't see the point of using the DC link to stop the path. So it is DC link indeed recreate the path. This algorithm won't make any sense. I mean, in this case, it won't be useful because it will try to solve something with a tool that doesn't solve this issue. So that won't be interesting.
So we really need a way that the links do not propagate the oscillations. They can propagate other disturbances. That's a comment I will make. I think that we have interconnected system has a lot of advantages. It has some disadvantages, which is the propagation of disturbances, but the experience shows that the interconnection had more benefits than it had disadvantages by far.
Also, one point that can be added is that the worst case, in a way, is we go back to is that we get back to the previous existing interior oscillation. And so in this point of view of small scale stability, we will not have gained anything, and it will be a pity. But this segmentation has so many other advantages that I've touched a bit, so maybe it's still a good thing. I like to say that segmentation can always, DC link can do at least as much as what can do an AC line. So even if we realize that we made a mistake in the exact placement of the DC segmentation, we still have one.
Okay, yeah, that was the final comment. I will just mention it here, no interaction needed. So in this idea of not only having a planning action, but maybe can be used in an operational environment, meaning that, well, sometimes it's good to have the interconnection, and you could do the AC emulation, and in some points of time it's not good. Operators have an experience that maybe in the morning hours it's beneficial to have an interconnection or not, and in the evening hours you would like to have a strict separation. Well, maybe we don't have to be so strict, even in the same with the if you open or close AC links. Okay, like in the Chinese example. Maybe in the Chinese example it was always a problem, but maybe it's not always a problem. And line openings happen. Not every line is opened every day, but many lines are opened every day. So it's an operation, at least in Spain, that is used quite a lot. Quite a lot. For another thing, for voltage control, but anything. Okay, thanks a lot for your patience with me, for the answers. Again, well done, congratulations. And soon you can enjoy.
Thank you very much.
Okay, thank you, Lukas. Well, it has been very interesting for me to follow all this discussion. And well, of course, I have to contribute a little bit, but not so much because also the time is advancing. First of all, I would like to join my colleagues into congratulating you and your supervisors for this very good work. I agree with them that it's a well-written document, a very good presentation, also that you are providing some contributions to this field, and also that you have one of these interesting ingredients, I would say, in research, which is to be a bit, let's say, provocative and to open, let's say, non-mainstream lines of research and revising some discussions. And I think that's very useful, and I think it's an attitude we have to keep all the time when working in research. So it's very good. At the same time, it is very difficult because then you have to convince a lot of people about many different things. But well, in any case, it's very interesting, and always you learn a lot from it. Also, I would like to thank the colleagues for inviting me to be part of this. It has been a very good experience until now to be part of this examination panel and to listen and to participate to the discussion. Also, in our case, we have been looking into, I could say, related topics, not exactly the same thing, but also looking at something, some different grids interconnected with converters, and it's good to see that there are some common topics, some very different topics. But I'm saying this also to motivate a bit my questions later, and also to make it, to put a bit of background on the questions. Because in our case, normally our reasoning is that the power system is perhaps evolving into more and more power electronics, less and less inertia in the system. Then there appear many interesting questions. All of us are working on these topics, and we have been discussion already on the grid forming, on the low inertia, on a number of new instabilities appearing in the network because of the coupling between converters, generators, lines, inductances, capacitors. Well, many new things can happen, and if they can happen, they will happen, and we should understand as much as possible. Okay, so in this context, there are lots of things to do. And also in this context, we are seeing that the grid is evolving, adding HVDC lines for the reasons discussed before, and also these HVDC converters can do an important role, right, in trying to provide more stability to the system, and we think this is an interesting topic. In the way you organized your main questions of research for this thesis, it's different. I'm not saying it's, of course, not worse, it's different, right, because you are starting more from the electromechanical oscillations, which indeed are a very important problem and indeed require a lot of research. but I would say they are not everything, right? They are part of the important things we have nowadays. And based on that, you have studied this HVDC as a solution to improve the stability when considering this kind of interactions in the system. And somehow all the formulation is based on the assumption that whatever it works for this electromechanical oscillations analysis, let's say, can be used, right? And somehow you follow the reasoning that, well, we have electromechanical oscillations in AC power systems. We use phasor modeling, right, RMS simulation for the analysis, and I understand also small signal analysis is based on that. And we analyze the system like this, right? Then we can add HVDC, but you used also for, I understood, some EMT simulation as well for validation, but I would say that the analysis is mainly based on phasor, right, on RMS simulation. Then I had here a fundamental doubt that in the original system, before the converters, everything RMS clearly is okay. When you add converters, depending on the solutions and how you are segmenting, you can add more or less, but in some cases you can have multiple converters. In some cases it's perhaps bipolar schemes, also converters. Sometimes these converters can be close to each other. And then the question is, in this system you are proposing to solve a previous oscillation, it is likely that there will appear new oscillations because of the solution proposed, but perhaps these ones have not been studied in the thesis because perhaps it will be another thesis or further work, right? And I wanted to ask you about this. What do you think about this? Can this solution bring additional problems or what?
So first, directly in this PhD, the only converters we had were the one of the DC links. So we had really little converters, so there was nearly no need to, there was really little need to study the interaction between them. And so the few DC link between the Nordic countries and the rest of the system are simulated by loads in our test system. So in this test system, there is little to no interaction between the converters because we have little of them. So in a more complex test system, with a system with already a lot of converters, adding even new ones may create interaction between them. And the more we have, the more interaction we can have, and also the proximity can increase the interaction. So there is a need to be careful about that. And the issue also is that the interactions depends mainly on the control of the VSC. So they need to be studied depending of which control we implement on the different VSC and how they interact against each other. Also maybe with some LCC converter in case there are some. So it's I think it's really a huge research topic, and it will necessarily bring some interaction if there are a lot and mainly close converters. But it could be mitigated by the control of the VSC. So there is a need for a research topic about the interaction between the converters, and depending on which the controllers will limit them, we can maybe limit the issue with the supplementary controllers.
Yeah, and a question also related to the discussion before. One of the comments from Professor Sigrist. In this case, if you can we, let's say, separate this like in two stages where like you analyze the larger electromechanical oscillations, you plan your segmentation, then you look at the system and you see, okay, perhaps I need further studies. And then I do as a second step these more detailed studies of interactions between converters. Could it be like this, or should we do all together in a in improving the methodology, adding this? What do you think?
So the initial goal on the methodology wasn't to do only small scene analysis. Initially, we were hoping to have some a criteria on a small scene analysis to give us some candidates for the segmentation. One for transstability to give us some candidates, and maybe to work on different power flow, and then compare all the candidates with different criteria. We wanted to stay in the context of the tree stability I've cited, and so definitely that's mean that if we want to do it all together, that means first we need to compare different candidates, but that's not an issue. Finding the candidate and so on, we can do it many different ways. I propose one, so it's different ways that could be used. So comparing different candidates is fine. But then, if we want to do it inside of the methodology with some optimization process, it means that we need to have, for each stability of interest, we need to have an easy to calculate criteria. And in the case of small signal stability, trend stability, and frequency stability, we thought about some that could be quite easy to calculate with linearized system, or at least really simplified system, and so that could be part of an optimization process. And so for interaction between the converters, I said I didn't study that much, so I'm not sure we can easily define a criteria that could be calculated with low computation time that for a given segmentation boundaries. So I think we will need to do one thing then the next. So define a segmentation boundaries candidate with some criteria, and then simulate and to check how the interaction on power system on converter will occur. But again, that depends so much on the supervised or the controller, on the control of the links, that it's hard to give a generic answer.
Yeah. Okay. Another question, very basic one, I am curious about, is about the validation of the small signal analysis you did. How did you validate? Did you do any validation of these results you obtained?
You mean of the result I have on the...
Yeah, the small signal model you have.
So I have two, in a way, I have two validations. The first one is a comparison between my two different way of linearize. Yeah. So the first one is with numerical numerization of Daimola, and the second one is with linear models and then the use of SSST. And so the results are not exactly the same, of course, but we have good, the difference are good enough compared to what we are used to. To compare to what we see in the literature when using different tools for the linearization. And the second one is the dynamic simulations.
Okay.
We see, we observe the interior mode in the ACC system and not in the segment system, and it's really not easy to see in the figure I gave you, but we also see the dumping of the local mode in the dynamic simulation. So our main conclusion on small scene analysis are also seen in the dynamic simulation. So we are quite optimistic about the result.
So you did time domain simulations with a nonlinear model and linear model, and checked that they were showing the same result?
The dynamic simulation was only with nonlinear simulations. And the small scene analysis.
So you check that the frequency of oscillation is the same?
Yes.
But not that exact time, the waveform is exactly the same? Okay.
Frequency and damping, more or less.
Yeah. Okay. Also, in all this debate on very interesting on the go for segmentation or not and so on, a curiosity I wanted to mention is that you know that normally there is an alpha link between Spain and France that was mentioned. Normally it's operated as an AC line to add a bit more. What do you think about that related to this research?
There's two different ways to answer. The first one is that the TSO are really conservative because the systems are too big to fail, so you cannot allow to test things test crazy things, crazy ideas, because there is too much at stake to take risk. So of course the TSO take as little risk as possible, and they are limited in their innovation. So that's why it's really natural to use IC line emulation. And then I think that it's also maybe a bit forced to do it, because not fully, but the DC line, because it's embedded in the system, it needs to follow the rules of an AC system fully. While in case of the segmentation, it won't be the case anymore. And that, I think, what brings so much advantages of the segmentation compared to only embedded DC link. So that's true. What I just said is perfectly. It's true for active power, and so for active power, you cannot do so much except small variation. Of course, for example, you cannot do frequency support stuff like that, because otherwise you will create loops in the power flow that will create more stability issue. However, we can also act on the reactive power, and actually I'm not sure of what are the reactive power implemented in the ELF line. That's something where there is, I think, a lot that could be done.
Yeah. Well, it was just more a comment on, because in the whole discussion it's a bit curious as well to see to see this, but yeah. Okay. Also, I have a comment on this interesting topic of the dominant paths, the algorithms you developed to identify it, and also all the discussion before with Jef and Lukas as well on the topic of also if we should identify all the paths and then do all the segmentations, as Jef mentioned before, or do it let's say one after the other, and then it was interesting to listen to this discussion. Also, Lukas mentioned the model reduction in his comment.
The what one?
Model reduction, that could be part of it, and perhaps if you reduce the model, then the path is passing through a reduced node, then you have to then zoom in the node and perhaps identify again the path inside, and also I had a note here on the topic. So I wanted to ask you about this model reduction, because it was mentioned by Lukas, but it was not clear to me if you used this or not, and if not, if you think it could be valuable to use it.
To reduce more the system, you mean? Or?
Yes, to reduce the order of the model, let's say the number of nodes, aggregate some nodes, and then identify the paths, and then perhaps zoom into this aggregating nodes and identify the subpath, we could call it, I don't know.
I think it could, for the test system I use, it's already quite simplified, the model, so reducing is more, won't change the result much. But for a complex system, well, for example, if we had the full grid of the full Nordic grid, we could perfectly, the algorithm could be applied to this a huge grid. The computation time is really short, so it's not an issue of computation time. But maybe actually, I don't think we'll have a big difference of result.
But actually, in the answer to Jef, you were saying that you can have a huge complexity, right, of branches and interconnections. So now you say it's simple, but perhaps not that simple, right? If there were many,
it's not that simple if you want to compare a lot of them.
Yeah. Which is what we want in this specific question.
If you want to find the dominant one, only one, whatever the complexity of the system, it will find one. And simplifying the model will allow to have less results. We can compare them and then get into more details into each result.
I can develop a bit more my question. I was referring more to the option mentioned that you could try to find all of them at the same time. And then also what I had noted here was that in addition to that, and it's further work I know for you, you want to study also multi-terminal systems, and perhaps a multi-terminal scheme could be given by that, right? for these branches with more than one terminal, more than two terminals, right? So the question was, in order to address this perhaps different problem, not in the scope of the thesis, if perhaps this model reduction could be useful. Because otherwise it's perhaps too complex, right, to study.
Yeah, model reduction will give a more broad place to segment. And then there's the question, how do we do it? So changing every lines or creating some kind of MTDC or supergrid in the region would be a solution.
Yeah. Well, I know it's not in the scope, but it's just when you listen about these interesting ideas, of course, all of us are thinking also some additional ones. Okay, then also another question related to my colleagues. I'm sorry, I'm being longer than I wanted to be initially, but this is because it's very interesting. Also another question related to what Marina and Jef mentioned before, and also Lukas, I think, and well, perhaps all of us, also Maider, on the topic of we have the system without HVDC, you have the electromechanical oscillations, you add HVDC to segment, but then also you add PODs, and then you come the oscillations with PODs, and then there is this general question, okay, could you do it in another way? Probably it's less expensive and so on. It was mentioned different, like from the generators, and well, I think it was mentioned different related ideas were mentioned from all the colleagues here. And the only one I wanted to add, I had this same comment here, and I think in the discussion it has been more or less clear, but I just wanted to add, for example, a StatComs as well, perhaps, because also you are using this POD for reactive power, or even a StatComs with the storage, but well, I just wanted to add a comment on this, right, that probably economically there are other ways to solve the problem which can be better, but I agree with your answer before to all the colleagues, which is okay, yes, but perhaps we will build HVDC lines anyway, and perhaps the system can grow and become segmented in some cases in a natural way, and perhaps the Iberian Peninsula is a good example. The Spanish system, as you explained, can be an example. So I think this has been more or less agreed. So yeah, I also had comments on the grid forming, but I think it's sufficient discussion on that and that topic. Yeah, and also on this, this question from Jef on the political parallelism. Also, it's curious to see how technology is sometimes related, right, to this. And probably we have also some other examples. I don't know, with these phase shifters and so on. Probably it's something relatively similar, more for the economic part, right? And also this is related, as it was said before, by Lukas, for the economics. And these economic paths as well, which were mentioned, it's interesting. And also how they could be related to the, I had here a note on the, now we are talking, in some countries, like in Nordic system, they have these prices of energy different for different zones. And I don't know if the electromechanical paths are related to them, because sometimes the prices change a lot when there are limitations in the constraints in the power flow, right? And perhaps these electromechanical oscillation paths can be somehow related. So it's well, and as Lukas suggested, you can do the PhD on economics. Yeah. Okay. Yeah. And with this, I finish with my comments. It was also interesting to discuss with you. I don't know if the colleagues in the examination panel have any additional comment. Yeah, probably it's better not to start that. And also, I would like to ask the audience if there is anyone in the room who wants to ask something or comment something or join the debate, or perhaps you are looking more forward to the lunchtime. Okay, in this. Nobody, right? Okay. In this case, we will close this part of the examination, right? Now we will deliberate. I don't know if here or we will go here in the room. So I have to ask you to leave the room. But we are not finishing with the examination, right? We will deliberate, and after deliberation, which hopefully it will be short, but well, we have to find some consensus also between the examination panel, but hopefully it will be short. Then we will tell you to enter the room again. Okay, so we ask you to leave, but please do not go very far away.
Thank you.
Yeah. Thank you. Okay. Okay, good. Then, well, after deliberation, perhaps long because of all the paperwork, but not because we had important disagreements. After the deliberation, after studying your work, listening to your presentation, and having the discussion with you, we all agreed that you deserve the maximum funding. Okay. So, and basically, we all agreed also, we appreciated the contributions of your work on this challenging topic and the answers you provided to the topics, perhaps which were not totally well or finished or presented in the work, but then in the discussion clarified absolutely everything. So yes, this is the mark, outstanding. And perhaps before the applause, just one last comment. You know that Lukas, in the beginning of the session, we have also an additional distinction of cum laude for the doctoral thesis. But to get this awarded, it needs to be an unanimous vote from all the members of the examination panel. Okay, and this has given to the university, and they will at some point next week or whenever. And the same for the best thesis award as it has been read. I'm doing also the translation because I don't know if everybody understood in the beginning the text. And well, yeah, with this, congratulations on this outstanding presentation. And yeah, I think with this we can close the event. I don't know how we are doing here, if somebody or whatever you. In every location is a bit different, so yeah, I don't know.
It's okay. Okay.
Yeah.
As much happy as you.
Okay.
Well done, Mathieu. Well done.
Yes. Thank you very much for
For you.
No.
And congratulations to you as well.
Congratulations, Javier.
Muchas gracias. Bueno.
Congratulations, Aurelio.
Aurelio,
Well done, Matthew.
Well
It was a
done.
pleasure.
Thank you.
Participate.
Thank you for asking stupid questions.
Huh?